Welcome back. Tonight, we settle in with the quiet, methodical life of Niels Bohr, the Danish physicist who spent his days pondering the strange behavior of atoms, wandering the halls of his Copenhagen Institute in thoughtful silence, pausing mid-sentence during conversations that stretched on for hours, as he searched, always searching, for precisely the right word to describe phenomena that seemed, at first glance, to defy description altogether, building a model of reality that was, in its own gentle way, stranger than anyone had imagined. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. On the 7th of October, in the year 1885, in a handsome apartment building situated along Vedstranden, which translates rather pleasantly to by the Strand, a street running alongside the canal in the heart of Copenhagen, a baby boy was born to Christian Bohr and his wife Ellen, and they named him Niels Henrik David Bohr, following the Danish custom of giving children several names to honor family and tradition. And this child, arriving on an autumn day when the light over the Danish capital would have been softening toward the longer shadows of the approaching winter, would grow to become one of the most significant figures in the history of physics, though on that particular October morning he was simply a newborn, wrapped in blankets, in a comfortable home in one of the oldest and most beautiful parts of Copenhagen, where the buildings lean gently toward the water and the city moves at its own unhurried pace. The apartment at Vedstranden occupied a privileged position in the city, close to Christiansborg Palace and the various seats of Danish governance and culture, and this location reflected the standing of the Bohr family within Copenhagen society, for they were not ordinary people by any conventional measure, but rather belonged to that rarefied class of intellectuals and professionals who shaped the cultural and scientific life of Denmark during the latter half of the 19th century. And young Niels would grow up surrounded by conversation, ideas, and the gentle assumption that thinking deeply about the world was simply what one did with one's time, much as other families might assume their children would take up farming or trade. Christian Bohr, the father, held the position of professor of physiology at the University of Copenhagen, and he was a scientist of genuine distinction, not merely someone who held an academic post, but a researcher who made contributions that would outlast his lifetime. And indeed, he was nominated twice for the Nobel Prize in Physiology or Medicine, which gives some indication of the regard in which his work was held by the international scientific community, though he never received the prize itself, as is the case with many deserving scientists throughout history, for there are always more worthy candidates than there are prizes to distribute, and the vagaries of committee decisions do not always align with the judgments of posterity. The elder Bohr's most significant scientific contribution was his discovery and description of what came to be known as the Bohr effect, which concerns the behavior of hemoglobin, that remarkable protein in our blood that carries oxygen from our lungs to our tissues and returns carbon dioxide in the other direction. And Christian Bohr demonstrated that the affinity of hemoglobin for oxygen changes depending on the concentration of carbon dioxide and the acidity of the surrounding environment, which might sound like a rather technical observation, and indeed it is, but it has profound implications for understanding how our bodies function, for it explains how hemoglobin can pick up oxygen efficiently in the lungs, where carbon dioxide levels are low, and release it readily in the tissues, where carbon dioxide levels are higher due to cellular metabolism. And this elegant mechanism is still taught in physiology courses around the world, still bearing the Bohr name, a quiet memorial to a scientist who worked carefully and observed closely. Christian Bohr conducted his research in laboratories at the university and brought the habits of scientific thinking into his home, not in the sense of turning his family life into an experiment, but rather in fostering an atmosphere where curiosity was valued and where asking questions about how things worked was considered entirely natural and worthwhile. And young Niels would have absorbed these attitudes simply by being present, by listening to his father discuss his work, by understanding from an early age that the natural world could be investigated systematically and that such investigation was a noble way to spend one's life. Ellen Adler Bohr, the mother, came from a background quite different from her husband's academic world, though no less distinguished in its own way, for her family was among the most prominent Jewish families in Denmark, wealthy and influential in the world of finance and banking, and her father, David Baruch Adler, generally known as DB. Adler had founded Privatbanken, which became one of the most important financial institutions in the country, and the Adler family occupied a position in Danish society that combined commercial success with cultural sophistication, for they were not merely people who made money, but people who used their resources to support the arts, to collect paintings, to build beautiful homes, and to participate in the intellectual life of their nation. Ellen herself was an educated and intelligent woman, though the opportunities available to women in academia during that era were severely limited regardless of their abilities, and she brought to her marriage and to her children not only the material comfort that her family's wealth could provide, but also a warmth and stability that would prove important in nurturing 3 children who would all go on to achieve remarkable things in their respective fields. For the Bohr household was not cold or austere despite its intellectual seriousness, but rather a place of genuine affection and support. The family home became known as a gathering place for some of the most interesting minds in Copenhagen, a kind of informal salon where scientists and philosophers and artists would come together for conversation and debate. And this tradition of intellectual hospitality was common among the educated classes of European cities during this period, a time when the boundaries between different fields of knowledge were more permeable than they would later become, and when a physiologist might find himself in animated discussion with a poet or a painter without anyone finding this particularly unusual, for there was still a sense that all knowledge was connected, that understanding the world required multiple perspectives, and that an evening spent in good conversation was among the most valuable ways one could spend one's time. Among the regular visitors to the Bohr household was the philosopher Harold Håfting, who was a close friend of Christian Bohr and who would later become an important influence on the young Niels, as he began to develop his own ideas about the nature of reality and the limits of human knowledge. And there were also physicists and mathematicians and physicians and various other figures from the University of Copenhagen, creating an environment in which a child could absorb, almost without noticing, the idea that the life of the mind was a rich and rewarding one, full of unsolved problems and ongoing debates and the pleasure of understanding something that had previously been obscure. Niels was not the only child in the household, for he had an older sister named Jenny, who had been born in 1883, 2 years before him, and a younger brother named Harold, who arrived in 1887, and the 3 children grew up together in this stimulating environment, each finding their own way through childhood and eventually into their adult lives, though it was the 2 boys who would achieve the greatest public recognition, not because Jenny lacked ability or intelligence, but because the opportunities available to women during that era remained frustratingly narrow, and many talented women of that generation lived lives of quiet accomplishment that history has not remembered as fully as it should. Harold Bohr, the younger brother, would grow up to become a mathematician of considerable distinction, making important contributions to the field of mathematical analysis, and particularly to the study of almost periodic functions, and he would hold a professorship at the University of Copenhagen just as his father had done, continuing the family tradition of academic excellence. But Harold was also gifted in another direction entirely, for he was an exceptional footballer, talented enough to play for the Danish national team, and he participated in the 1908 Olympic Games in London, where the Danish team won a silver medal, finishing second to Great Britain. And this combination of mathematical brilliance and athletic prowess made Harold something of a celebrity in Denmark, beloved for his football skills and respected for his scholarly work. And the two brothers would remain close throughout their lives, supporting each other and collaborating intellectually even as their fields diverged. The Bohr family also maintained a summer residence, a country house called Narration, located in the pleasant countryside north of Copenhagen, and this property provided a retreat from the city during the warmer months, a place where the children could play outdoors, explore the natural world, and enjoy the freedom that comes with space and fresh air. And these summers in the country would have been formative experiences, offering a counterbalance to the more formal atmosphere of the city home and the school year, and allowing the Bohr children to develop in ways that urban life alone might not have permitted. From an early age, Niels displayed what might be called a mechanical aptitude, a fascination with how things worked and a willingness to take things apart in order to understand them. And family stories that have been passed down describe the young boy fixing clocks and repairing various household items, displaying a patience and persistence that would later characterize his approach to scientific problems. For he was not the sort of child who gave up easily when faced with a puzzle, but rather one who would keep working at something until he understood it, turning it over in his mind, trying different approaches, and eventually arriving at a solution through sheer determination. This mechanical inclination was not necessarily unusual for a child growing up in a household where scientific thinking was valued, but it suggested a particular kind of intelligence, one oriented toward understanding the physical world in concrete terms rather than purely abstract ones. And this combination of theoretical and practical abilities would serve Niels well in his later career as a physicist. For the best scientists often possess both the capacity for abstract mathematical reasoning and an intuitive feel for how physical systems actually behave. And the young boy tinkering with clocks in 19th-century Copenhagen was already developing this dual capacity, though he could not have known where it would eventually lead him. In 1891, when Niels was approaching his 6th birthday, he began his formal education at Gammelholm Latin School, which was one of the traditional grammar schools of Copenhagen, the kind of institution that provided a classical education to the sons of the educated and professional classes, with a curriculum that emphasized Latin and Greek, literature and history, mathematics and the sciences, preparing students for eventual entry into the university and the learned professions. And here Niels would spend the next decade of his life, moving through the grades at the steady pace that such schools demanded, absorbing knowledge, making friends, and gradually developing into the young man who would eventually transform our understanding of the atom. The experience of school was not uniformly easy for Niels. However, for despite his obvious intellectual gifts and his ability to grasp complex ideas, he struggled with certain aspects of the curriculum, particularly with writing and composition, finding it difficult to express his thoughts clearly and correctly on paper. And this difficulty persisted throughout his school years and indeed throughout his life, for Bohr would always find writing challenging, preferring to work out his ideas through conversation and dictation rather than through solitary writing. And some scholars have suggested that this pattern may indicate a form of what we would now call dyslexia, a neurological difference that affects the processing of written language without diminishing overall intelligence or capability. Whether or not Niels had what would now be diagnosed as a specific learning difference, It is clear that there was a gap between his evident brilliance in understanding concepts and his ability to communicate those concepts in written form. And this gap must have been frustrating for a young student in a school system that placed great emphasis on written examinations and essays, though he found ways to compensate, relying on his verbal abilities and on the support of family and eventually of colleagues who could help him shape his thoughts into written form. And this pattern of collaborative thinking and writing would become a hallmark of his later scientific work, conducted not in isolation but through constant dialogue with students and colleagues. The years of early childhood in Copenhagen, from his birth in 1885 through to the mid-1890s when he was establishing himself as a student at Gammelholm Latin School, were years of formation and absorption, years in which the raw materials of his character were being assembled. And while it would be many years before Niels Bohr would make the contributions that would earn him a place in the history of science, the foundations were being laid in those quiet Copenhagen rooms, in the conversations he overheard, in the clocks he repaired, in the summers at Nærumgaard, and in the sometimes difficult work of learning to express his thoughts through the written word. And all of this was happening in a city and a country at peace, in a family that provided both intellectual stimulation and emotional security, creating conditions that allowed a remarkable mind to develop at its own pace, without undue pressure, in the gentle rhythms of a Danish childhood that would be remembered with fondness throughout a long and productive life. In the autumn of 1896, when Niels Bohr was 11 years old, he began his studies at Gammelholm Latin School, which stood in the heart of Copenhagen not far from the canals and the old merchant houses that gave that part of the city its particular character. The school was a classical gymnasium in the European tradition, which meant that its curriculum placed great emphasis on Latin and Greek, on Danish composition and the careful study of grammar, on history and literature and all those subjects that were thought to cultivate the mind of a young gentleman in preparation for university studies. Niels would spend the next 7 years within these walls, walking each morning through streets that grew familiar with the seasons, past the same shopfronts and the same neighbors going about their business, into classrooms where the light fell through tall windows and where masters stood before blackboards covered in conjugations and declensions. It became apparent quite early in his time at Gammelholm that young Niels possessed a mind that worked in particular ways that did not always align neatly with what his teachers expected or what the curriculum demanded. In subjects such as Latin and Greek, where success required the memorization of vocabulary and the mastery of grammatical rules, he performed adequately but without distinction. His spelling in Danish was notably poor, and his compositions, while thoughtful in content, often contained errors that his teachers found vexing. There is something rather comforting in knowing that a mind which would later reshape our understanding of the atom could not always remember where to place its commas or how to spell certain common words. Language, it seemed, did not arrange itself in his thoughts with the same natural order that he found elsewhere, and his essays sometimes wandered in ways that frustrated instructors who preferred more linear arguments and tidier conclusions. But in mathematics and in physics, something quite different emerged. Here was a realm where Niels found not only competence but genuine joy, a place where his particular way of thinking, which moved slowly and carefully and always sought the foundations beneath the surface, could flourish without the arbitrary rules of spelling or the irregular verbs of ancient languages to trouble him. He would work through problems with a patience that sometimes surprised his classmates, unwilling to move forward until he truly understood each step, each principle, each underlying assumption. This was not the quickness that some teachers mistake for brilliance, but rather a deeper engagement, a refusal to accept anything merely on authority without first satisfying himself that it made sense, that it connected properly to everything else he knew. His physics teacher at Gammelheim was a man named Christian Christensen, and it is worth pausing here to appreciate the role that such teachers play in the lives of young people who are still discovering what sort of minds they possess. Christensen had himself been a student of some distinction, and he brought to his teaching a genuine love of the subject and an ability to recognize potential in his pupils. He noticed something in young Niels Bohr, something in the way the boy approached problems, in the questions he asked, in his unwillingness to be satisfied with superficial answers. A good teacher sees not just what a student knows but how a student thinks, and Christensen became an early mentor to Niels, encouraging his interests and perhaps helping him to understand that the difficulties he faced in languages did not diminish the remarkable capacities he demonstrated elsewhere. Alongside his academic studies, Niels and his younger brother Harold discovered a passion that had nothing to do with books or laboratories, a passion that took them outdoors into the fresh air of Copenhagen, onto grass pitches where young men gathered to kick a leather ball and test themselves against one another. Football, or soccer as it is known in some parts of the world, had been growing in popularity across Europe during these years, and the Bohr brothers took to the sport with considerable enthusiasm. They joined Akademisk Boldklub, a club associated with the university and popular among students and academics, where they could play alongside others who shared their interests both intellectual and athletic. Niels played as goalkeeper, which is perhaps a fitting position for someone of his temperament. The goalkeeper stands apart from the constant motion of the field, watching, waiting, reading the patterns of play as they develop, and then responding with sudden decisive action when the moment demands. It requires patience and concentration, the ability to remain alert through long periods when nothing much happens, and then to perform precisely when everything depends upon it. Whether Niels was an exceptional goalkeeper or merely an enthusiastic one is difficult to say from this distance, but he played regularly and with evident enjoyment, finding in the sport a balance to his studies and a way to spend time with his brother that required no books and no blackboards. Harold, the younger brother, proved to be the more talented footballer of the two. He played in the outfield, where his speed and skill made him a valuable member of the team. The two brothers remained close throughout these years, companions in sport as they were companions in intellectual pursuits, and their shared experiences on the football pitch added another dimension to a relationship that would remain important to both of them throughout their lives. In 1908, some years after the period we are now considering, Harold would be selected to play for the Danish national team at the Olympic Games in London, where Denmark would face the host nation in the final match and earn the silver medal. Niels did not reach such heights in football, but he continued to play for some years, and the sport remained a pleasant memory of his youth, a time when the body's movements mattered as much as the mind's calculations. In 1903, at the age of 17, Niels Bohr matriculated at the University of Copenhagen to study physics. He was young for a university student, though not exceptionally so, and he entered an institution that his father knew well and where the family name carried a certain respect. The University of Copenhagen was not a large institution by the standards of the great European universities, but it possessed a faculty of genuine distinction and a tradition of serious scholarship. For a young man interested in physics, it offered both solid training in the fundamentals and exposure to the latest developments in a field that was, during these very years, beginning to undergo transformations that no one yet fully understood. Among the professors who shaped his early university experience was the same Christian Christensen who had taught him at Gammelheim, for Christensen held a position at the university as well. This continuity must have been reassuring to the young Niels, providing a familiar presence as he adjusted to the greater demands and freedoms of university life. Christensen's lectures were known for their clarity and their attention to experimental foundations, and he continued to encourage his former pupil as Niels began to engage with physics at a more advanced level. The relationship between a gifted student and a perceptive teacher can be one of the most important factors in intellectual development, and Niels was fortunate to have such a relationship spanning both his secondary and his university education. But the influence that shaped Niels most profoundly during these years came not from the university lecture halls but from his own home, from the presence of his father Christian Bohr and the remarkable intellectual environment that Christian had created. The Bohr household had long been a gathering place for thinkers of various kinds, and the discussions that took place in Christian study or around the family dinner table exposed young Niels to ways of thinking about science and philosophy that went far beyond what any curriculum could offer. Christian Bohr was a physiologist of genuine accomplishment, known particularly for his work on the oxygen-carrying properties of blood, and he brought to his home life the same rigor and curiosity that characterized his laboratory research. In Christian's laboratory, young Niels had opportunities to observe scientific work in progress, to see how experiments were designed and conducted, how data was gathered and interpreted, how theories were tested against the stubborn facts of nature. This exposure to scientific methodology, experienced not through textbooks but through direct observation of his father's work, gave Niels an understanding of how science actually proceeds that many students acquire only much later, if at all. He learned that scientific knowledge is not simply received but constructed, that it emerges from a dialogue between human minds and natural phenomena, that it requires patience and humility and a willingness to follow the evidence wherever it leads. Among the regular visitors to the Bohr household was a philosopher named Harold Håfting, who was a close friend of Christian Bohr and one of the most respected thinkers in Denmark at that time. Håfting was interested in epistemology, which is the branch of philosophy concerned with the nature and limits of human knowledge, and his conversations with Christian often touched on questions about what we can truly know about the world and how we can justify our claims to knowledge. Young Niels was permitted to listen to these discussions and eventually to participate in them, and he found himself drawn to philosophical questions that would later inform his thinking about the strange new physics of the atomic world. Håfting conducted seminars at the university on epistemological topics, and Niels attended these seminars with genuine interest, unusual for a physics student who might have been expected to focus more narrowly on his own discipline. The questions that Håfting raised about the relationship between observation and reality, about the role of the observer in shaping what is observed, about the limits of what can be said meaningfully about the world, planted seeds in Niels's mind that would bear fruit decades later when he grappled with the interpretation of quantum mechanics. The philosophical training he received in these years gave him tools for thinking about foundational questions that many of his fellow physicists lacked, and it contributed to the distinctive character of his later contributions to physics. In 1905, when Niels was 19 years old, an opportunity arose that would mark his first significant engagement with original scientific research. The Royal Danish Academy of Sciences and Letters announced a prize competition, inviting submissions on a particular topic in physics. The subject for that year's competition concerned the surface tension of liquids, specifically the investigation of liquid jets and the vibrations that occur in them. This was a problem that required both theoretical analysis and experimental skill, and it was the sort of challenge that allowed a young scientist to demonstrate genuine capability rather than merely the ability to pass examinations. Niels took up this challenge with characteristic thoroughness. The problem of surface tension in liquid jets involved understanding how liquids behave when they flow through narrow openings, how they form droplets, how vibrations propagate through them, and how all of this could be described mathematically. It was a classical problem in physics, connected to the work of earlier scientists like Lord Rayleigh, but there remained aspects that were not fully understood and measurements that had not been made with sufficient precision. For the experimental portion of his work, Niels needed to create apparatus that could produce liquid jets of controlled properties and instruments that could measure their behavior accurately. He worked on this project for many months, and much of this work took place in his father's laboratory, where he had access to equipment and to the guidance of experienced experimentalists. The laboratory became a second home to him during this period, a place where theory met practice and where the abstractions of mathematical physics had to answer to the concrete realities of actual substances behaving in actual ways. He learned the frustrations that every experimental scientist knows: the equipment that does not work as expected, the measurements that refuse to agree, the long hours of repetitive labor required to gather enough data to draw meaningful conclusions. When Niels submitted his work to the Academy, it was recognized with the gold medal, the highest award the competition offered. This was a significant achievement for such a young scientist, and it announced to the Danish scientific community that Christian Bohr's son possessed abilities that marked him for a distinguished career. The work itself was solid rather than revolutionary, a careful contribution to an established area of physics rather than a dramatic breakthrough, but it demonstrated that Niels could carry a substantial research project through to completion and that his understanding of physics extended beyond what he had been taught in lectures. The years at university continued, and Niels progressed through his studies with growing confidence and deepening engagement. But the life of a family, even a happy one, contains its sorrows, and in 1911, tragedy visited the Bohr household. His sister Jenny, who had been part of the household throughout his childhood and youth, died. The circumstances of her death brought grief to the entire family, a reminder that the pursuit of knowledge and the achievements of the mind do not protect us from the losses that come to every human life. For Niels, the death of his sister was a profound emotional blow. Jenny had been a presence in his life for as long as he could remember, part of the fabric of home and family that had supported him as he grew and developed. Her absence left a gap that could not be filled, a silence where her voice had been. Grief of this kind shapes a person in ways that are difficult to trace but impossible to ignore, adding depth to the character and perhaps a certain seriousness to the understanding of life's brevity and preciousness. In the years that followed, Niels would rarely speak publicly of this loss, but those who knew him well understood that it had marked him, had become part of who he was. In the year 1905, when Niels Bohr was still a young man of 19, the Royal Danish Academy of Sciences and Letters announced a prize competition, as they did from time to time, inviting submissions on a particular topic of scientific interest. The subject chosen for that year concerned the surface tension of liquids, specifically the behavior of water when it emerges from a tube in the form of a jet, and the Academy wished to receive papers that might advance the understanding of this gentle, everyday phenomenon. Surface tension, you see, is that quality which causes water to bead upon a leaf, or allows a small insect to walk upon the surface of a pond without sinking, and it arises from the way molecules at the surface of a liquid are drawn inward by their neighbors, creating something like a delicate elastic skin. When water flows from a narrow tube, this surface tension shapes the emerging jet in particular ways, causing it to break into droplets at predictable intervals, and the physicists of the time were interested in understanding the precise mathematics governing these oscillations and instabilities. The young Bohr, still an undergraduate at the University of Copenhagen, decided to enter this competition, and he set about conducting experiments with characteristic thoroughness. He had available to him an unusual advantage, for his father Christian Bohr held the chair of physiology at the university, and the elder Bohr's laboratory contained equipment suitable for delicate experimental work. And so Niels found himself spending long hours in that physiological laboratory, surrounded by apparatus designed for the study of living systems, repurposing what he could for his investigation of water jets. The work required careful measurement of very small phenomena, the precise timing of oscillations, the observation of droplet formation under controlled conditions, and young Bohr approached these tasks with the same methodical attention he would later bring to far more abstract questions. One detail from this period speaks to the practical, hands-on nature of his early scientific education. Finding that he needed glass tubes of particular dimensions and specifications that were not readily available, Bohr learned to blow his own glass apparatus. This is a skill that requires patience and a steady hand. The heating of glass rods over a flame until they become soft and workable, the careful shaping of tubes and vessels through breath and manipulation, and Niels became sufficiently proficient that he could produce the equipment his experiments demanded. There is something rather lovely in this image of the future architect of atomic theory, still a student, seated at a workbench with a flame before him, fashioning glass tubes through which water would flow for the purpose of measuring surface tension. The distance between such humble, practical work and the abstract heights of quantum mechanics seems very great, and yet the same qualities of persistence and careful observation served him in both endeavors. The paper that Bohr eventually submitted to the competition went considerably beyond what the Academy had perhaps anticipated. Beginning with the existing theoretical framework established by the English physicist Lord Rayleigh, who had done foundational work on the oscillations of liquid jets some decades earlier, Bohr extended the mathematical treatment to encompass situations that Rayleigh's analysis had not fully addressed. He considered the effects of viscosity, that property which makes some liquids flow more sluggishly than others, and he developed corrections to the existing theory that brought predictions into closer agreement with experimental observations. The young man's paper demonstrated not merely competence in applying established methods but genuine creativity in pushing beyond them, identifying where the existing theory was incomplete and working out the necessary refinements. The Royal Danish Academy awarded Bohr the gold medal in 1907, when he was 21 years of age. This was a significant honor for so young a scientist, a recognition from the senior members of the Danish scientific establishment that here was a talent deserving of attention. The winning paper was subsequently published in the Transactions of the Royal Society of London, bringing Bohr's name to the attention of the broader international scientific community for the first time. The subject itself, the behavior of water jets, might seem far removed from the atomic physics with which Bohr would later become associated, yet there are subtle connections. The careful mathematical analysis of physical phenomena, the willingness to extend theory when experiment reveals its limitations, the combination of laboratory skill with theoretical insight. These are approaches that served him throughout his career, whatever the particular question at hand. Following this early success, Bohr continued his studies at the University of Copenhagen, and in 1909 he completed the requirements for his master's degree. The Danish educational system of that era differed somewhat from the arrangements familiar in other countries, and the master's degree represented a substantial achievement, requiring both coursework and original research. Having reached this milestone, Bohr turned his attention to the question of what subject he might pursue for his doctoral dissertation, and after consideration he settled upon a topic that was then occupying many of the finest minds in physics, namely the electron theory of metals. To understand what this meant, one must recall that the electron itself had been identified as a constituent of matter only a dozen years earlier, in 1897, when the English physicist J.J. Thomson had demonstrated that cathode rays consisted of tiny particles carrying negative electrical charge. This discovery had opened vast new territories for exploration, and physicists were working to understand how these electrons might explain the various properties of different materials. Metals, in particular, presented an interesting case. Everyone knew that metals conduct electricity far better than other substances, and it seemed natural to suppose that this conductivity arose from electrons moving freely through the metallic material. Similarly, metals conduct heat very efficiently, and they possess that characteristic luster we associate with polished silver or copper, and theorists hope to explain all these properties through a coherent account of how electrons behave within metallic structures. The most developed version of such a theory had been put forward by the German physicist Paul Drude around the turn of the century, and it had been refined by the Dutch physicist Hendrik Lorentz, who applied the methods of statistical mechanics to the problem. The Drude-Lorentz model, as it came to be known, imagined the electrons within a metal as behaving rather like molecules in a gas, bouncing about randomly, colliding with the fixed atoms of the metal lattice, and responding to applied electrical fields by drifting in a particular direction. This model achieved some notable successes, explaining the relationship between electrical and thermal conductivity that had been observed experimentally, but it also encountered difficulties, places where its predictions did not match what measurements revealed, and these discrepancies hinted at something fundamentally incomplete in the classical picture. Bohr immersed himself in this subject with extraordinary dedication. He read widely in the existing literature, mastering the mathematical techniques employed by Drude and Lorentz and others, and he set about examining the foundations of the theory with meticulous care. What he found, through this extended analysis, was that the problems with the electron theory of metals were not merely technical difficulties that might be resolved through clever calculation. Rather, they pointed to deep inconsistencies between the behavior one would expect from classical physics and the behavior that nature actually exhibited. The classical theory predicted, for instance, that metals should have certain magnetic properties arising from the motion of their electrons, and these predictions did not agree with experiment. Similarly, the theory made predictions about how the specific heat of metals, the amount of energy required to raise their temperature by a given amount, should depend upon the electrons, and again the predictions failed. Bohr worked on his doctoral dissertation over the course of several years, and the document he eventually produced, titled Studies on the Electron Theory of Metals, was completed in 1911. It was a substantial piece of work, running to over 100 pages, and written entirely in Danish, which was the customary language for dissertations at the University of Copenhagen. This choice of language, natural enough within its context, had consequences that Bohr could not have fully anticipated. The international scientific community conducted its business primarily in German, French, and English, and a dissertation written in Danish would reach only a limited audience. Many of the insights Bohr had achieved, the penetrating criticisms he had developed of the classical electron theory, remained largely unknown outside Scandinavia for years afterward, and other physicists would sometimes independently reach conclusions that Bohr had already carefully worked out. The dissertation itself is a remarkable document, dry and technical in the manner of such works, yet containing within its careful analysis the seeds of ideas that would later flower into quantum mechanics. Bohr demonstrated, with mathematical rigor, that certain phenomena simply could not be explained within the framework of classical physics. He showed that the existing theory led to contradictions and impossibilities, that the electrons in a metal could not behave in the way classical mechanics said they must behave if the observed properties of metals were to be accounted for. This was, in its quiet way, a revolutionary finding, though Bohr did not yet possess the new concepts that would be needed to resolve the contradictions he had identified. He was, as it were, clearing the ground, demonstrating the inadequacy of the old foundations without yet knowing what would replace them. The defense of the dissertation took place on the 13th of May, 1911, and by all accounts it was a notably brief affair. The customary procedure involved the candidate presenting and defending their work before a committee of examiners, responding to questions and criticisms, in a formal ceremony that could extend for some hours. In Bohr's case, the defense lasted only about an hour and a half, which was considered quite short. The examiners, it seems, found little to challenge in the work. The argument was clear, the mathematics sound, and there was not a great deal to dispute. One of the examiners later remarked that the dissertation was of such quality that he had difficulty finding substantive objections to raise, and so the defense concluded more quickly than was typical. This professional triumph was shadowed, however, by personal loss. Niels Bohr's father, the physiologist Christian Bohr, had fallen ill, and in February of 1911, just 3 months before Niels defended his dissertation, Christian died. He was only 55 years of age, and his death came as a profound blow to the family. Christian had been not merely a father but an intellectual companion to his sons, a model of scientific dedication, and his laboratory had provided the space where Niels had conducted those early experiments on surface tension. The household at Vedstranden, where the Bohr family had lived in such comfortable intellectual fellowship, would never be quite the same. Niels completed his doctorate in the months following his father's death, carrying forward the work even through grief, and one imagines that the brevity of the dissertation defense, whatever its formal causes, might have been something of a mercy under the circumstances. Amid the demands of doctoral research and the sorrow of loss, there was also joy in these years. In 1910, Niels Bohr became engaged to Margrethe Norland, a young woman whose family he had come to know through various Copenhagen connections. Margrethe was the daughter of a pharmacist, and her brother Niels Erik Norland was a mathematician of some distinction who had been a student alongside Bohr at the university. The two families moved in similar circles, educated and cultured, and the young couple had found in each other a companionship that would prove to be one of the most enduring and sustaining relationships in either of their lives. Margrethe was intelligent, warm, and possessed of a quiet strength, and she would become Niels's closest confidant, his support through decades of scientific labor and public responsibility. Their engagement marked the beginning of a partnership that lasted until Bohr's death more than half a century later, and those who knew them spoke of the marriage as exceptionally happy, a union of genuine affection and mutual respect. And so the years from 1906 to 1911 represent a period of formation, a time when Niels Bohr moved from talented student to credentialed scientist, winning recognition for his experimental skill, developing his abilities as a theoretical analyst, and establishing the personal relationships that would sustain him in the years ahead. The gold medal for his work on surface tension demonstrated his capacity for original research. The doctoral dissertation revealed his ability to identify fundamental problems in existing theory, and his engagement to Margrethe provided an anchor of personal happiness amid the abstractions of physics. He had lost his father but gained a partner, completed a significant piece of scientific work while recognizing that the deepest questions remained unanswered, and stood ready, at the age of 25, to venture beyond Denmark and engage with the wider world of international physics. The dissertation written in Danish would limit his immediate influence, but the problems he had identified, the inadequacies of classical physics he had so carefully documented, would soon enough find their resolution in ideas that Bohr himself would help to create. In the early autumn of 1911, Niels Bohr arrived in England carrying with him a fellowship from the Carlsberg Foundation, that Danish brewing enterprise whose profits had long been directed toward the support of scientific and cultural endeavors in Denmark. He was 25 years old, recently awarded his doctorate, and he had come to Cambridge with the intention of working alongside Joseph John Thomson, the man who had discovered the electron some 14 years earlier, and who presided over the Cavendish laboratory with the quiet authority of one who had fundamentally altered humanity's understanding of matter itself. Bohr had prepared carefully for this meeting, as he prepared carefully for most things, and he had brought with him not only his doctoral dissertation but also a copy of Thomson's influential book on the conduction of electricity through gases, a work he had studied with considerable attention during his years in Copenhagen. The September weather in Cambridge was mild enough, and the ancient colleges with their stone walls and manicured lawns presented a picture of scholarly permanence that might have impressed a young visitor from Scandinavia. Bohr found lodgings and made his way to the Cavendish Laboratory, that somewhat unremarkable building on Free School Lane where so much of modern physics had taken shape over the preceding decades. He had written ahead to announce his arrival, and Thomson had agreed to receive him, though the older physicist was occupied with numerous responsibilities and could not have been expected to devote extensive attention to every foreign student who appeared at his door seeking guidance. When Bohr was finally admitted to Thomson's presence, he came bearing his dissertation and the annotated copy of Thomson's book, and it was here that the meeting took an unexpected turn, one that Bohr himself would later recall with a mixture of embarrassment and philosophical acceptance. For Bohr, in his earnest and thorough way, proceeded to point out several passages in Thomson's book where he believed he had identified errors, places where the mathematical reasoning seemed to him incomplete or where the physical conclusions did not quite follow from the premises. He did this not from any desire to embarrass or challenge the great man, but simply because he had noticed these things and assumed that Thomson would wish to know about them, much as one might helpfully point out a smudge on a colleague's spectacles. Thomson's response was cordial but distinctly cool. He was a man of considerable accomplishment who had received the Nobel Prize in Physics in 1906, and while he was not necessarily averse to criticism, he perhaps did not expect it to arrive in quite this form from a young Danish physicist who had only just stepped off the boat. The errors Bohr had identified may or may not have been genuine errors, and Thomson showed little inclination to examine them in detail. He thanked Bohr for his interest, made some polite remarks about the dissertation, and that was more or less the extent of their substantive engagement. In the weeks and months that followed, Bohr found his time at Cambridge somewhat unsatisfying. Thomson remained courteous but distant, offering little in the way of collaboration or direction. Bohr attended lectures, worked on improving his English, which was serviceable but not yet fluent, and spent long hours in the laboratory attempting to conduct experiments on cathode rays, work that did not proceed particularly well owing in part to his limited experience with experimental apparatus. He was a theorist by temperament and training, more comfortable with equations and conceptual arguments than with the delicate manipulation of glass tubes and vacuum pumps, and the months at Cambridge began to feel like a period of marking time rather than genuine progress. But then came December of 1911, and with it an invitation that would alter the entire trajectory of Bohr's scientific life. He travelled to Manchester to visit the laboratory of Ernest Rutherford, the New Zealand-born physicist who had recently proposed a revolutionary new model of the atom. Rutherford was a large, energetic man with a booming voice and a temperament quite different from the reserved Thomson. He had received his own Nobel Prize in 1908, awarded for chemistry rather than physics owing to his work on radioactive transformations, and he had since turned his attention to the structure of the atom itself, conducting experiments that involved firing alpha particles at thin gold foils and observing how they scattered. The results of these scattering experiments, carried out primarily by Hans Geiger and Ernest Marston under Rutherford's direction, had been startling. Most of the alpha particles passed straight through the gold foil as though it were not there, but a small fraction bounced back at large angles, some of them nearly reversing direction entirely. Rutherford had famously compared this to firing artillery shells at tissue paper and having them bounce back at you. The only explanation that made sense was that the atom was not the uniform blob of positive charge that Thomson had imagined, with electrons embedded in it like raisins in a pudding, but rather a structure in which almost all the mass was concentrated in a tiny, dense nucleus at the center, with the electrons orbiting at relatively great distances in the empty space surrounding it. This nuclear model of the atom was elegant and compelling, but it presented a serious problem that Rutherford himself was well aware of. According to classical electromagnetic theory, an electron orbiting a nucleus should continuously radiate energy, spiraling inward and collapsing into the nucleus in a fraction of a second. The atom, according to the physics that everyone knew and trusted, should not be stable at all. Matter should not exist in the form that it manifestly did exist. This was not a minor difficulty to be smoothed over with small adjustments, but rather a fundamental crisis that called into question the applicability of classical physics to the atomic realm. Bohr was captivated. Here was a problem worthy of his abilities, a puzzle that combined experimental results with deep theoretical challenges, and Rutherford himself was a vigorous and encouraging figure who seemed genuinely interested in what his younger colleagues had to say. The contrast with Thomson could hardly have been more pronounced. By March of 1912, Bohr had arranged to transfer from Cambridge to Manchester, and he took up residence in a city that was quite different from the dreaming spires of the older university town, a place of industry and manufacturing where the atmosphere was thick with the smoke of countless chimneys and the streets were crowded with workers and merchants going about their business. The Manchester laboratory was a lively place, filled with researchers from various countries who worked on problems related to radioactivity and atomic structure. Hans Geiger was there, the German physicist who had developed the counter that bears his name for detecting individual particles of radiation. Ernest Marston was there as well, the young man who had actually performed many of the scattering experiments that led to the nuclear model. And there was Georg von Heversche, a Hungarian chemist who would later win his own Nobel Prize and who became one of Bohr's closest lifelong friends. The atmosphere was collegial and stimulating, with regular discussions and debates about the meaning of experimental results and the direction of future research. Bohr threw himself into this environment with enthusiasm. He worked on understanding the behavior of alpha particles as they passed through matter, losing energy through countless small interactions with the electrons of the atoms they encountered. But his mind kept returning to the fundamental problem of atomic stability, the question of why electrons did not simply spiral into the nucleus as classical theory demanded. He began to formulate ideas, tentative at first, about how quantum concepts might be applied to the structure of the atom, drawing on the work that Max Planck had done a decade earlier on the radiation emitted by hot objects, In June of 1912, Bohr prepared a memorandum for Rutherford outlining his thoughts on the stability problem and related questions. This document, which Bohr later referred to simply as the Rutherford Memorandum, contained the seeds of what would become his revolutionary model of the atom, though the full flowering of these ideas would not come until the following year. The memorandum was lengthy and detailed, perhaps too detailed for Rutherford's taste, as the older physicist was known to prefer concise communications and had little patience for extended theoretical arguments. Nevertheless, Rutherford recognized that Bohr was grappling with important questions, and he offered encouragement even if he did not fully engage with all the technical details. As the summer of 1912 approached, Bohr prepared to return to Denmark. His fellowship period was coming to an end, and there were personal matters that required his attention. Chief among these was his engagement to Margrethe Norland, the sister of a mathematician friend, a young woman of intelligence and warmth whom Bohr had come to love deeply during his years in Copenhagen. They had corresponded throughout his time in England, long letters in which he shared his scientific thoughts and his personal feelings with equal openness, and she had provided a steady source of support and understanding even from a distance. On the 1st of August, 1912, Niels Bohr and Margrethe Norland were married in a civil ceremony at the town hall in Slagelse, a small city on the island of Zealand where Margrethe's family had connections. The wedding was a quiet affair, as suited both their temperaments, without elaborate religious ceremony or extensive social display. From this day forward, Margrethe would be Bohr's constant companion, his confidant, and his collaborator in a sense that went beyond the conventional role of a scientist's wife. She would help him draft his papers, typing and retyping manuscripts as he endlessly revised his thoughts, serving as a first reader and a gentle critic who helped him clarify his often convoluted prose. The honeymoon took the newlywed couple first to Norway, where they could enjoy the dramatic fjords and mountain landscapes that provided such a contrast to the flat Danish countryside, and then to England, where Bohr could revisit Manchester and continue his discussions with Rutherford and his colleagues. It was a journey that combined personal happiness with ongoing scientific work, as was characteristic of Bohr's approach to life, in which the boundaries between work and everything else were never sharply drawn. Returning to Copenhagen, Bohr took up a position as a teaching assistant at the university, a relatively modest appointment that nevertheless allowed him to continue his research while earning a living. He was working now with increasing intensity on the problem of atomic structure, and the memorandum he had prepared for Rutherford was evolving into something more comprehensive and more radical. The key insight, the crucial connection that would transform his tentative ideas into a coherent theory, came in the early months of 1913. What Bohr realized, in a moment of clarity that emerged from months of preparatory thought, was that the frequencies of light emitted by atoms, those characteristic spectral lines that had been catalogued by physicists for decades without anyone fully understanding their origin, were directly connected to the quantum behavior of electrons within the atom. The work of Johann Balmer and others had established that the spectral lines of hydrogen followed precise mathematical patterns, but no one had explained why. Bohr saw that if electrons could only occupy certain discrete orbits around the nucleus, corresponding to specific quantized energy levels, and if they emitted light of a definite frequency when they jumped from one orbit to another, then the observed spectral patterns would follow naturally. This was a profound departure from classical physics, which allowed for continuous variation in energy and position. In Bohr's model, certain orbits were simply forbidden, and electrons could not spiral smoothly inward but could only make sudden jumps from one allowed state to another. The atom was stable not because classical theory permitted stability, but because the quantum rules prevented the continuous radiation that would otherwise occur. It was a bold hypothesis, supported by the remarkable agreement between its predictions and the known spectral lines of hydrogen, and it would establish Bohr as one of the foremost physicists of his generation. In the summer of 1913, Niels Bohr was 27 years old, and he was about to change the way human beings understood the structure of matter itself, though of course he could not have known the full extent of what he was beginning. And perhaps that is often the way with discoveries, that they arrive not as thunderclaps but as careful papers submitted to scientific journals, written in precise language, offering ideas that seem at first simply interesting, and only later reveal themselves to be the foundation stones of entirely new ways of thinking about the physical world. The journal in question was the Philosophical Magazine, a British publication with a long and respectable history in the sciences, and between July and November of that year, Bohr published 3 papers there, papers that would come to be known among physicists as his Great Trilogy, though at the time they were simply contributions to an ongoing conversation about atomic structure, a conversation that had been growing more urgent ever since Ernest Rutherford had proposed his nuclear model of the atom just 2 years before. Rutherford's atom, you may recall, consisted of a tiny dense nucleus at the center, carrying positive electrical charge, with electrons orbiting around it at some distance, rather like planets orbiting the Sun. And this was a tremendous insight, supported by beautiful experimental evidence. But it had a very serious problem, a problem that Bohr set out to address in these 3 papers. And the problem was this: according to the classical physics that James Clerk Maxwell had developed in the 19th century, an electron moving in a curved path around a nucleus should continuously radiate electromagnetic energy, and as it radiated this energy, it should spiral inward toward the nucleus, losing more and more energy as it went, until finally it collapsed into the nucleus itself, and this entire process should take only a tiny fraction of a second, which meant that according to classical physics, atoms should not be stable at all. They should collapse almost immediately, and yet here we all are, made of atoms that have persisted for billions of years, which suggests rather strongly that something was missing from the classical picture. What Bohr proposed was something quite radical, though he presented it in his characteristically careful and methodical way, building his arguments step by step, and the central idea was this: electrons in an atom do not behave the way classical physics says they should. They do not spiral inward radiating energy continuously. Instead, they exist in what Bohr called stationary states, specific orbits at specific distances from the nucleus. And while an electron remains in one of these stationary states, it does not radiate any energy at all. It simply continues in its orbit without losing anything, which is why atoms can be stable, why they do not collapse, why matter can exist in the persistent way that it so evidently does. Now this was a very strange idea, because it seemed to violate the well-established laws of electromagnetism, and Bohr was quite aware of this strangeness. He did not try to explain why electrons should behave this way. He simply proposed that they did, as a kind of fundamental postulate, and he showed that if you accepted this postulate, along with a few others, you could explain a great deal about how atoms actually behaved, how they absorbed and emitted light, and most impressively, you could explain the specific colors of light that hydrogen atoms produced when heated or electrified. The second key idea in Bohr's trilogy concerned what happened when an electron moved from one stationary state to another, and here Bohr introduced the concept that would become known as the quantum jump, though he did not use that exact phrase himself. And the idea was this: An electron could not gradually drift from one orbit to another. It could only make a sudden transition, jumping from one stationary state to a different stationary state. And when it made such a jump, it either absorbed or emitted a specific quantity of energy, a quantum of energy, in the form of light, and the amount of energy involved was determined by the difference between the two stationary states, the one the electron was leaving and the one it was arriving at. This meant that atoms could only emit or absorb light of very specific energies, very specific colors, and this explained something that had puzzled physicists for decades: the fact that when you looked at the light from heated hydrogen through a spectroscope, you did not see a continuous rainbow of colors. You saw only specific lines at specific wavelengths, a pattern that a Swiss schoolteacher named Johann Balmer had described mathematically back in 1885, fitting the wavelengths to a simple numerical formula, though no one had been able to explain why that formula worked. Bohr showed that his model of the atom, with its stationary states and quantum jumps, predicted exactly the pattern that Balmer had discovered. The mathematics fell into place with remarkable precision, and this was tremendously compelling, because here was a theory that not only explained why atoms were stable, but also predicted, to a high degree of accuracy, the specific wavelengths of light that hydrogen atoms actually emitted, wavelengths that had been measured very carefully in laboratories. And the agreement between theory and experiment was quite good indeed. The third paper in the trilogy extended these ideas to consider how atoms might combine into molecules, and how the electrons in atoms might be arranged in different shells or groups, ideas that would later prove important for understanding chemical bonding and the periodic table of elements, though this part of Bohr's work was more speculative and would require considerable development by other scientists in the years to come. The response to Bohr's papers was, as you might expect, mixed, and many of the older physicists who had spent their careers developing and applying classical physics found the ideas difficult to accept, not because the mathematics was wrong, but because the underlying assumptions seemed so arbitrary, so disconnected from the familiar principles that had served physics so well for so long. Why should electrons be restricted to these particular orbits and no others? Why should they not radiate energy continuously as Maxwell's equations said they must? What physical mechanism prevented them from doing so? And Bohr had no answers to these questions. He could only say that this is how nature appeared to behave, and that the agreement with experiments supported his postulates, even if he could not explain them more deeply. But not everyone was skeptical, and one of the most enthusiastic responses came from Albert Einstein, who had himself been one of the pioneers of quantum thinking with his work on the photoelectric effect, and Einstein recognized immediately the significance of what Bohr had done. The way he had taken the quantum ideas that had been floating around somewhat uncertainly and applied them directly to the structure of the atom, producing concrete predictions that could be tested against experiment. And Einstein is reported to have said, upon learning of Bohr's work, that it was one of the most beautiful results he had ever seen. A high compliment indeed from someone whose own standards for physical beauty were exacting. During these years, Bohr's personal life was also growing and changing, and in 1916 his wife Margrethe gave birth to their first son, whom they named Christian, and this was the beginning of what would become a large family. Niels and Margrethe would eventually have 6 sons altogether, though tragedy would touch them as well. 2 of their sons would die young, one in a boating accident and one from illness. But all of that lay in the future, and in these early years there was simply the joy of a young family beginning, of a household filling with the sounds of children. Professionally, Bohr was also putting down roots in his native Denmark, and after spending time at Manchester working with Rutherford, he returned to Copenhagen. and in 1916 he was appointed to a newly created position, the first professor of theoretical physics at the University of Copenhagen, the first such chair in all of Denmark. And this was a recognition of both his growing reputation and the importance of the new physics that he was helping to create. These were the years of the First World War, and though Denmark remained neutral throughout the conflict, the war nonetheless affected the scientific community profoundly. International communication became difficult. Travel between countries was restricted or impossible. Colleagues who had worked together and corresponded freely found themselves cut off from one another, and the normal exchange of ideas that is so vital to scientific progress was severely impaired. German scientists could not easily communicate with British scientists, and the international character of physics, which had seemed so natural before the war, was badly damaged. Bohr continued his work as best he could under these conditions, and during the war years he was already beginning to think about establishing an institute of his own, a place dedicated to theoretical physics where researchers could come to work and think and discuss ideas together. And he began negotiations with the Danish government and with the Carlsberg Foundation, which had been established by the famous brewing family to support science and culture in Denmark. And these negotiations took time, as such things always do, but they were ultimately successful, and by the end of the decade the plans were in place for what would become the Institute for Theoretical Physics, later renamed the Niels Bohr Institute, which would become one of the most important centers of physics in the world during the 1920s and beyond. Meanwhile, Bohr was continuing to develop his theoretical ideas, and in the years between 1918 and 1920, he articulated what became known as the correspondence principle, which was a way of connecting the new quantum physics with the older classical physics that it seemed to contradict. And the basic idea was this: whatever the quantum theory predicted, it should, in certain limiting cases, agree with what classical physics predicted, because classical physics had been tested and verified in countless experiments. It clearly worked very well for describing the behavior of large objects and certain kinds of phenomena. So any new theory, however revolutionary, should reduce to the old classical theory in the appropriate limits. This correspondence principle was not just a philosophical nicety. It was a powerful tool for developing new theoretical ideas, because it provided a constraint, a check, on what kinds of quantum theories could be correct. If a proposed quantum theory did not have the right classical limit, if it did not reduce properly to classical physics in the cases where classical physics was known to work, then something must be wrong with it. And this principle guided Bohr and others as they continued to develop atomic theory in the years that followed. During these years, Bohr also began to gather around him a group of younger physicists who were drawn to Copenhagen by his reputation and his ideas. And among the first and most important of these was Hendrik Kramers, a Dutch physicist who arrived in Copenhagen in 1916, becoming Bohr's first assistant. And Kramers was brilliant and energetic, and he would work closely with Bohr for many years, helping to develop and extend the theory of atomic structure, contributing ideas of his own, and also helping Bohr to write and revise his papers, which often went through many drafts as Bohr struggled to express his subtle ideas in clear language. This pattern of gathering talented young physicists around him, of creating a community where ideas could be freely discussed and developed, would become one of Bohr's most important contributions to physics, because science is not just a matter of individual geniuses having brilliant insights. It is also a matter of conversation and collaboration, of people thinking together and testing each other's ideas. And Bohr had a remarkable gift for creating environments where this kind of thinking could flourish, where young scientists felt encouraged to speak their minds and challenge established ideas, including Bohr's own ideas. And the Institute for Theoretical Physics, when it finally opened in 1921, would become the most famous example of this gift, but the pattern was already established in these earlier years, with Kramers and others gathering around Bohr in Copenhagen. And so by 1920, as the First World War receded into the past and the scientific community began to rebuild its international connections, Niels Bohr had established himself as one of the leading figures in theoretical physics. He had proposed a revolutionary model of the atom that explained the stability of matter and the patterns of spectral lines. He had developed the correspondence principle to guide the further development of quantum theory. He had secured a professorship and begun the process of creating his own research institute. And he had started to build around himself a community of brilliant young physicists who would help to carry the quantum revolution forward in the remarkable decade that was about to begin. On the 3rd of March, in the year 1921, a rather modest building on a quiet street in Copenhagen opened its doors for the first time, and in doing so, it became one of the most important places in the entire history of physics, though you would not have known it from looking at the building itself, which was pleasant and functional but not particularly grand, situated on Blegdamsvej, which is a street that runs along the edge of Faldparken, a large public park where people walk their dogs and children played on the grass, and the building had been constructed with funds gathered from various sources, including a generous contribution from the Carlsberg Foundation, which you may recognize as being connected to the brewery of the same name, because in Denmark there has long been a tradition of private philanthropy supporting scientific research, and additional money came from private donors and from the Danish government, all of whom believed that Niels Bohr deserved a proper institute where he could pursue his investigations into the nature of atoms and train the next generation of theoretical physicists. And so the Institute for Theoretical Physics came into being, though people would eventually call it simply the Bohr Institute, because it was so thoroughly shaped by his presence and his way of thinking about problems. The building itself was arranged in a practical manner, with the scientific work taking place on the lower floors, where there were offices and a library and rooms for seminars and discussions, and blackboards everywhere because theoretical physicists are deeply attached to their blackboards, finding them essential for working through calculations and explaining ideas to one another. And the upper floors were given over to living quarters for the Bohr family, so that Niels and his wife Margrethe and their children made their home directly above the institute, which meant that the boundary between domestic life and scientific life was wonderfully blurred, with young physicists from around the world sometimes finding themselves invited upstairs for dinner, or encountering the Bohr children on the stairs. And this arrangement suited Bohr perfectly because he was not the sort of person who believed in strict separations between work and life, preferring instead a more organic flow where ideas could be discussed at any hour and where the atmosphere was more like an extended family than a formal academic institution. Margrethe Bohr played a role that was absolutely essential, though often overlooked, because she managed the household and created an environment of warmth and hospitality that made visiting scientists feel welcome and cared for. And she also served as a kind of intellectual sounding board for her husband, listening patiently as he worked through difficult concepts, and helping him to articulate his ideas more clearly, because Bohr was famous for his difficulty in putting thoughts into words, often circling around an idea many times before finding the right way to express it. And Margrethe understood this about him and provided the calm, supportive presence that allowed him to think. And the visiting physicists came to appreciate her kindness and her ability to make the institute feel like a genuine community rather than merely a workplace. The stream of brilliant young visitors began almost immediately and continued throughout the 1920s. Turning the institute into what many would later describe as the world capital of atomic physics. And among the most notable of these visitors was Werner Heisenberg, who first came to Copenhagen in 1924, arriving as a young man of 22 who had already shown remarkable talent, but who had not yet made the discoveries that would make him famous. And Heisenberg found in Bohr both a mentor and a kind of intellectual father figure, someone who took his ideas seriously and pushed him to think more deeply about the foundations of physics, and their relationship would prove extraordinarily fruitful for the development of quantum mechanics, though that story unfolds gradually over several years. Other remarkable young physicists made their way to Blegdamsvage during this period, including Wolfgang Pauli, who was known for his sharp critical intelligence and his willingness to tell anyone, including Bohr himself, when he thought their ideas were wrong, which Bohr actually appreciated because he valued honest intellectual engagement above politeness. And Paul Dirac came from Cambridge, a quiet and precise young Englishman whose mathematical abilities were extraordinary, and Hendrik Kramers from the Netherlands, who became one of Bohr's closest collaborators, and John Slater from the United States, and many others whose names are less well known but who contributed to the remarkable atmosphere of creativity and discovery that characterized the Institute during these years. The way of working that developed at Copenhagen came to be known as the Copenhagen spirit, though no one sat down and deliberately created it. Rather, it emerged organically from Bohr's personality and his beliefs about how physics should be done. And the essential feature of this spirit was intense collaborative discussion, often lasting for many hours, where ideas were examined from every possible angle and nothing was accepted simply because an authority figure said it was true. And Bohr himself was famous for never being satisfied with an explanation, always asking one more question, always probing deeper into the foundations of an idea to see whether it truly made sense. And this could be exhausting for the younger physicists who work with him. But it was also exhilarating because they felt they were participating in something genuinely important, the attempt to understand the fundamental nature of physical reality. The discussions often continued during long walks, because Bohr was fond of walking and found that ideas came more freely when he was moving. And so he would take young physicists on rambling excursions through the parks of Copenhagen or along the harbour, talking all the while about the problems of atomic physics, and these walking discussions became legendary among the physicists who participated in them, sometimes going on for many hours until everyone was quite tired, but still somehow energized by the intellectual exchange. And in the summers, Bohr would sometimes invite colleagues to his country house at Tisvilde, on the coast north of Copenhagen, where the discussions could continue in a more relaxed setting with the sea nearby and the Danish summer light lasting well into the evening hours. There were also games of ping-pong, which Bohr played with great enthusiasm though perhaps not with great skill. And these games served a useful purpose because they allowed the mind to rest from the intensive concentration required for physics, while still maintaining the informal social atmosphere that was so important to the Copenhagen spirit. And Bohr believed quite sincerely that the best physics emerged not from isolated individuals working alone in their offices, but from communities of people thinking together, challenging each other, building on each other's ideas. And the Institute was designed, both physically and socially, to encourage exactly this kind of collaborative work. In November of 1922, Niels Bohr received the Nobel Prize in Physics for his work on the structure of atoms and the radiation they emit, which was recognition of the atomic model he had developed nearly a decade earlier and the subsequent elaborations and applications of that model. And the prize came as no great surprise to anyone in the physics community because Bohr's contributions were widely recognized as being of fundamental importance. And he traveled to Stockholm for the ceremony on the 10th of December, which is the anniversary of Alfred Nobel's death and the traditional date for the prize ceremonies. And he delivered his Nobel lecture on the 11th of December, speaking about the structure of atoms and explaining the ideas that had led him to his model of electron orbits and energy levels, speaking in his characteristic way, which was thoughtful and careful, taking time to acknowledge the contributions of others and to place his own work in the broader context of the development of physics. The following year, 1922, was also notable for a happy event in the Bohr family, the birth of another son, Arj, who arrived in June, and though no one could have known it at the time, this child would grow up to become a physicist himself, and in 1975 he would receive his own Nobel Prize in Physics for work on the structure of atomic nuclei, making the Bohrs one of the very few families in history to have produced two Nobel laureates in physics, father and son. Though of course in 1922 little Arj was merely a baby sleeping in his crib on the upper floors of the institute, while downstairs the brilliant young visitors argued about quantum theory. In 1924, Bohr collaborated with Kramers and Slater on a theoretical proposal that would become known as the BKS theory, after the initials of its three authors, and this theory attempted to address some of the deep puzzles surrounding the interaction of light and matter by proposing something quite radical, namely that energy might not be strictly conserved in individual atomic processes but only conserved on average when many processes were considered together, which was a dramatic departure from one of the most fundamental principles of physics, the law of conservation of energy, which had stood unchallenged for decades. And the BKS theory also proposed that atomic transitions occurred in a somewhat statistical way, guided by what they called virtual radiation fields, and the theory was certainly creative and represented a serious attempt to grapple with the very real problems facing atomic physics at the time. However, experiments carried out by Walther Bothe and Hans Geiger in Germany, and independently by Arthur Compton and Alfred Simon in the United States, soon demonstrated that the BKS theory could not be correct, that energy and momentum were indeed conserved in individual atomic processes and not merely on average, and so the theory had to be abandoned, which might seem like a failure, and in a narrow sense it was. But in a broader sense, the BKS theory served an important purpose because it stimulated thinking about the fundamental issues and helped to clarify what any successful theory of quantum mechanics would need to explain. And Bohr himself was not particularly dismayed by the refutation of the theory, accepting the experimental verdict with equanimity and turning his attention to new approaches. The year 1924 also brought Werner Heisenberg to Copenhagen for an extended visit, and during this time the relationship between Bohr and the young German physicist deepened considerably, with Bohr recognizing in Heisenberg a quite exceptional talent and Heisenberg finding in Bohr the kind of profound thinker he had been seeking, and they spent many hours in discussion, walking through Copenhagen and talking about the problems of atomic physics. And on one occasion they took a hiking trip together in the Danish countryside. Though Denmark is not known for its mountains, so this was more of a gentle ramble than a strenuous climb. And during these walks they discussed the deepest questions facing physics, such as what it really meant to describe the motion of an electron inside an atom, and whether the classical concepts of position and velocity could truly be applied to such tiny objects. And these conversations planted seeds that would bear fruit the following year. In 1925, Heisenberg, now back in Germany but still in close contact with Bohr and deeply influenced by their discussions, made a breakthrough of extraordinary importance, developing what would become known as matrix mechanics, which was the first complete and mathematically consistent version of quantum mechanics. And this work represented a radical departure from classical physics, abandoning the attempt to visualize electrons as little balls following definite paths, and instead focusing entirely on the observable quantities, the frequencies and intensities of light emitted by atoms, and describing these using mathematical objects called matrices, which are arrays of numbers that follow specific rules for multiplication and addition. And Heisenberg's matrix mechanics was strange and unfamiliar, but it worked, giving correct predictions for the behavior of atoms. and Bohr was deeply gratified that his young protege had achieved this breakthrough, feeling that the long discussions in Copenhagen had contributed to preparing Heisenberg's mind for this leap of understanding. The Institute on Blegdamsvage continued to thrive throughout this period, with more visitors arriving each year, drawn by the reputation of Bohr and by the exciting atmosphere of discovery. And the discussions continued, and the ping-pong games continued, and the long walks continued. And slowly, piece by piece, the new quantum mechanics was being assembled, with contributions from many different physicists working at different institutions, but with Copenhagen serving as a kind of intellectual hub where ideas were tested and refined, and where the meaning of the new physics was debated with an intensity found nowhere else. And Bohr himself was at the center of all this activity, guiding and questioning and encouraging, not always contributing specific calculations, but always asking the fundamental questions that kept everyone focused on what really mattered, which was not just getting the right answers, but understanding what those answers meant for our picture of the physical world. In the autumn of 1927, Niels Bohr stood before an audience of distinguished physicists at a conference in Como, Italy, gathered to commemorate the centenary of Alessandro Volta's death, and there, in that September gathering among the lakes and mountains of northern Italy, he introduced for the first time a concept that had been forming in his mind through years of careful thought, a principle he called complementarity, which would become one of the most profound and gently unsettling ideas in the history of physics, though unsettling in the quietest possible way, like discovering that a familiar room has always had a window you somehow never noticed before. The complementarity principle addressed something that had been troubling physicists since the early days of quantum theory, which was the strange behavior of light and matter at the smaller scales, where things seem to behave sometimes as waves spreading out through space and interfering with one another in the manner of ripples on a pond, and at other times as particles, discrete little packets of energy moving along definite paths like very small billiard balls. And the puzzle was how anything could be both of these things at once, since waves and particles seem to be such different sorts of entities altogether. Bohr's answer, delivered in his characteristically careful and measured way in that Como lecture hall, was that wave and particle were not contradictory descriptions of the same thing seen from the same angle, but rather complementary descriptions that applied in different experimental situations, and that the apparent contradiction arose only when one tried to apply both descriptions simultaneously, which nature did not permit, since the experimental arrangements required to observe wave behavior and those required to observe particle behavior were mutually exclusive, so that you could set up your apparatus to see interference patterns characteristic of waves, or you could set up different apparatus to detect individual particles arriving at definite locations, but you could never do both at the same time with the same experimental arrangement. This was not a statement of human limitation or incomplete knowledge, Bohr insisted, but rather a fundamental feature of nature itself, a reflection of how the quantum world actually works, where the kind of question you ask determines the kind of answer you receive, and where certain pairs of questions simply cannot be asked together, not because we lack cleverness, but because the questions themselves become meaningless when combined, rather like asking what is north of the North Pole. The Como lecture was important, but it was the fifth Solvay conference in Brussels just 1 month later, in October of 1927, that would become the setting for one of the most remarkable intellectual exchanges in the history of science, when Bohr and Albert Einstein began their legendary debates about the meaning and completeness of quantum mechanics, debates that would continue for years and would shape the way generations of physicists thought about the fundamental nature of reality. The Solvay conferences were invitation-only gatherings of the world's leading physicists, funded by the Belgian industrialist Ernest Solvay, and the fifth of these conferences, held at the Hotel Metropole in Brussels, brought together an extraordinary collection of minds, including Einstein, Bohr, Max Planck, Werner Heisenberg, Erwin Schrödinger, Louis de Broglie, Max Born, Wolfgang Pauli, and Paul Dirac, among others, and the official topic was electrons and photons. But the real subject that dominated the corridors and dining rooms was the interpretation of the new quantum mechanics and whether the strange probabilistic description it offered was truly complete. Einstein, who had done so much to create quantum theory through his work on the photoelectric effect and light quanta, was deeply troubled by the direction the theory had taken, particularly by the Copenhagen interpretation that Bohr and Heisenberg had developed, which seemed to abandon the classical ideal of a reality that exists independently of observation, with particles having definite positions and momenta whether anyone looks at them or not. And Einstein felt that this could not be the final word, that behind the statistical predictions of quantum mechanics, there must be some deeper, more complete description of nature. And so, over breakfast and during walks between sessions and late into the evenings, Einstein would devise thought experiments, clever imaginary arrangements of apparatus designed to show that quantum mechanics must be incomplete or inconsistent, and each morning he would present these challenges to Bohr, who would spend the day and often much of the night thinking them through, pacing and muttering and drawing diagrams, until by the next morning he could explain, patiently and thoroughly, where Einstein's reasoning had gone astray. One of Einstein's early challenges involved the single-slit and double-slit experiments, which demonstrate the wave nature of particles like electrons, and Einstein suggested ways that one might, in principle, determine which slit a particle went through while still observing the interference pattern that requires the particle to behave as a wave going through both slits at once, thus catching quantum mechanics in a contradiction. But Bohr showed each time that the very act of determining which slit the particle passed through would necessarily disturb the system enough to destroy the interference pattern, so that the complementary descriptions could never both be obtained in the same experiment. These debates were intense, and participants recalled the emotional atmosphere of those Brussels meetings, with Einstein endlessly inventive and Bohr endlessly patient, the two men circling each other intellectually like dancers who have practiced together for years, each knowing the other's moves yet still surprised by the occasional novel step. And through it all there was a deep mutual respect, even affection, despite their fundamental disagreement about what physics should ultimately tell us about the world. 3 years later, at the 6th Solvay Conference in 1930, Einstein arrived with what he believed was an unanswerable challenge, an ingenious thought experiment involving a box filled with photons, which came to be known as Einstein's photon box or light box experiment. And this time the target was not wave-particle duality but rather the Heisenberg uncertainty principle, which states that one cannot simultaneously know both the energy of a system and the precise time at which it has that energy, at least not beyond a certain limit of precision. Einstein's imaginary box had a shutter controlled by a clock inside the box, designed to release exactly one photon at a precisely known time. And by weighing the box before and after the photon's release, Einstein argued, one could determine the photon's energy with arbitrary precision using the famous equation relating mass and energy, thus knowing both the time of emission and the energy of the photon to whatever accuracy one wished, in apparent violation of the uncertainty principle. Bohr was deeply troubled by this argument, and witnesses recalled that he spent the evening in considerable distress, discussing the problem with colleagues and struggling to find the flaw in Einstein's reasoning, and for a time it seemed that perhaps Einstein had finally succeeded. But by the next morning Bohr appeared with a triumphant refutation, and the delicious irony was that his answer depended upon Einstein's own theory of general relativity. Bohr pointed out that the act of weighing the box required placing it in a gravitational field, and according to general relativity, a clock that moves in a gravitational field, as the box must when being weighed, runs at a different rate than a stationary clock, so that the very precision of the weighing introduced an uncertainty in the timing. And when Bohr worked through the mathematics carefully, he showed that the gravitational time dilation introduced exactly enough uncertainty to preserve the Heisenberg relation, and Einstein was forced to concede the point, though he never fully accepted that quantum mechanics was the final word. The debates would continue for years, reaching another famous peak in 1935 with the Einstein-Podolsky-Rosen paradox. But through all of it, the two great physicists maintained their friendship and their respect for each other's intellect, disagreeing about the deepest questions while agreeing that those questions mattered immensely and deserved the most careful thought one could give them. Meanwhile, during these years of philosophical debate, the Institute for Theoretical Physics in Copenhagen continued to flourish and expand under Bohr's leadership, becoming ever more firmly established as the world center for quantum physics, a place where young theorists from every country came to learn and contribute and argue in the best possible way. Among the visitors in this period was Lev Landau, the brilliant young Soviet physicist who arrived in Copenhagen in 1930 and impressed everyone with his quick mind and sharp tongue, and Felix Bloch from Switzerland, who came in 1931 and would go on to make fundamental contributions to solid-state physics, and George Gamow, the irrepressible Ukrainian theorist known for his wild sense of humor and his ability to explain complex ideas with whimsical illustrations and amusing stories. It was Gamow who began working with Bohr in 1928 on a new model of the atomic nucleus, treating it not as a rigid structure but as something more like a liquid drop, with the protons and neutrons held together by nuclear forces in much the same way that water molecules are held together in a droplet by surface tension. And this liquid drop model would prove remarkably useful in understanding nuclear properties and would later play a crucial role in explaining nuclear fission, though that discovery was still a decade in the future. The model captured something essential about the nucleus, how it could vibrate and deform and eventually break apart if disturbed enough, and while it was not a complete theory, it provided a framework for thinking about nuclear processes that complemented the more detailed quantum mechanical treatments. Another example of how Bohr valued having multiple perspectives on a problem, different ways of looking at the same phenomenon that could illuminate different aspects of its behavior. Throughout this period of intense scientific activity, Bohr's personal life continued in its quietly happy way, with his sons growing up in the comfortable family home and spending summers at the country house in Tisvilde, a small village on the north coast of Zealand where the Bohr family had a summer retreat among the dunes and forests near the sea. The Tisvilde house became a cherished refuge from the pressures of the Institute, a place where Bohr could walk on the beach and sail and spend time with his children, and where Margrethe could tend her garden and enjoy a slower pace of life than the constant stream of visitors and discussions that filled their Copenhagen home. And the boys grew up knowing both worlds, the intellectual intensity of their father's work and the peaceful simplicity of summer holidays by the water. In 1933, Bohr was elected president of the Royal Danish Academy of Sciences and Letters, a recognition of his standing not only in physics but in Danish intellectual life more broadly, and he took this role seriously, working to promote science in Denmark and to maintain international scientific connections during a period when political tensions were beginning to make such connections more difficult. There is a small anecdote from this period that reveals something of Bohr's personality and his gentle sense of humor. For visitors to his country house noticed that he had a horseshoe mounted above his door, the traditional symbol meant to bring good luck, and when one visitor, surprised to find such a superstitious object at the home of a great scientist, asked whether Bohr actually believed in the power of the horseshoe, Bohr replied that of course he did not believe in such things, but he had been told that it works whether you believe in it or not. This little joke, told with the dry wit that Bohr was known for, captures something about his approach to ideas generally, his willingness to hold multiple perspectives at once, his understanding that the universe might not care whether our theories about it are elegant or whether they match our expectations about how things ought to be, and his recognition that sometimes the most interesting truths are the ones that surprise us. The 1930s were years of accomplishment and recognition for Bohr, but they were also years of gathering shadows in Europe, as the political situation in Germany deteriorated and refugee scientists began to appear at the Institute. And Bohr, with his deep commitment to international cooperation in science and his fundamental decency as a human being, would soon find himself drawn into efforts to help those fleeing persecution, though that is a story for another time. For now, in these years between 1927 and 1935, the picture is one of intense intellectual activity, of debates with Einstein that pushed both men to think more carefully about the deepest questions in physics, of an institute that drew brilliant young scientists from around the world, and of a family life that provided warmth and stability amid all the excitement of revolutionary physics, the kind of balanced existence that Bohr seemed to manage with the same grace that he brought to reconciling wave and particle, holding complementary aspects of life together in a harmonious whole. In the middle years of the 1930s, as Niels Bohr moved through his 50th year and beyond, his attention turned increasingly toward the behavior of atomic nuclei, those dense central regions where nearly all the mass of an atom resides, packed into a space many thousands of times smaller than the atom itself. The nucleus had been discovered by Ernest Rutherford more than 2 decades earlier, and in the intervening years physicists had learned that it was composed of protons and neutrons held together by forces of extraordinary strength, forces that operated only across the tiniest distances and whose precise nature remained somewhat mysterious. Bohr brought to this problem his characteristic way of thinking, which sought always to find the simplest physical picture that could capture the essential behavior of a system, and in 1936 he proposed what came to be known as the compound nucleus model, a way of understanding nuclear reactions that would prove remarkably fruitful in the years to come. The compound nucleus model arose from Bohr's contemplation of what happens when a particle, such as a neutron, strikes an atomic nucleus. The previous way of thinking about such collisions had imagined the incoming particle interacting with just one or perhaps a few of the particles within the nucleus, much as a billiard ball might strike another ball on a table and set it moving while the other balls remained largely undisturbed. But Bohr proposed something quite different, suggesting that when a particle enters a nucleus, its energy is very rapidly shared among all the constituent protons and neutrons, creating what he called a compound nucleus in an excited state. This compound nucleus, having absorbed the incoming particle and distributed its energy throughout its entire structure, would then exist for a brief time, a time that was nevertheless long compared to the time it would take a particle to simply pass through, before eventually releasing its excess energy by emitting one or more particles or gamma rays. This picture had a certain elegant simplicity to it, and it explained many features of nuclear reactions that had previously seemed puzzling. In particular, it helped to account for the observation that nuclear reactions often produced results that seemed to have little memory of exactly how the compound nucleus had been formed, as though the intermediate excited state had thoroughly mixed up the energy before deciding how to release it. Bohr worked on developing this model with a young Danish physicist named Fritz Kalka, who had come to the Institute in Copenhagen as a research assistant and proved to be a valuable collaborator. Together, Bohr and Kalka explored the mathematical details of the compound nucleus theory, working out how the excited states might be expected to behave and how this behavior would manifest in the probabilities of various nuclear reactions occurring. Fritz Kalka was a thoughtful young man with considerable mathematical ability, and his collaboration with Bohr produced important papers that established the compound nucleus model on a firm theoretical foundation. Sadly, Kalka's promising career would be cut short, but during these years of the mid-1930s his contributions helped shape the direction of nuclear physics research at Copenhagen. The work he did with Bohr on the statistical properties of excited nuclear states represented a significant step forward in understanding how energy was distributed within the nucleus, treating the many protons and neutrons somewhat like molecules in a drop of liquid, each interacting strongly with its neighbors but the whole system exhibiting collective properties that could be described in simpler terms. This liquid drop analogy proved particularly valuable and became known as the liquid drop model of the nucleus. Bohr had long appreciated the power of physical analogies, and he recognized that a nucleus, with its densely packed particles held together by short-range attractive forces, behaved in many ways like a tiny droplet of liquid held together by surface tension. A liquid drop has a certain characteristic energy associated with its surface, and it can vibrate and oscillate in various ways. And if given enough energy, it can split apart into smaller droplets. The same, Bohr realized, might be true of atomic nuclei, and this seemingly simple insight would soon prove to have consequences of enormous significance. The years rolled forward, and the physics community continued its steady accumulation of knowledge about the atomic nucleus. Experiments were performed in laboratories across Europe and America, and theories were refined and extended. Then, in December of 1938, something unexpected emerged from a laboratory in Berlin. The German chemist Otto Hahn, working with Fritz Strassmann, had been bombarding uranium with neutrons and carefully analyzing the products, expecting to find elements only slightly lighter or heavier than uranium itself. Instead, to their considerable puzzlement, they found barium, an element with an atomic weight roughly half that of uranium. This result seemed impossible according to everything that was known about nuclear reactions, and Hahn wrote to his former colleague Lise Meitner, who had been forced to flee Germany earlier that year because of her Jewish heritage and was now living in Sweden. Lise Meitner received Hahn's letter and was spending the Christmas holiday at a small resort village in Sweden called Kungälv, where she had been joined by her nephew, Otto Frisch. Frisch was himself a physicist who had worked at Bohr's Institute in Copenhagen before taking a position in England, and he had come to visit his aunt for the holiday. Together, on a now famous walk through the snowy Swedish countryside, Meitner and Frisch worked out what must have happened in Hahn's laboratory. Using Bohr's liquid drop model, they realized that the uranium nucleus, when struck by a neutron, could become unstable and divide into two roughly equal pieces, much as a liquid drop can pinch apart into two smaller droplets. They calculated that this process would release an enormous amount of energy that came from the conversion of a small amount of mass according to Einstein's famous equation. Frisch suggested calling this process fission, borrowing a term from biology where it describes the division of living cells. After this revelation in Sweden, Otto Frisch hurried to Denmark to share the news with Bohr. It was still the Christmas holiday period, and Bohr was at his family's country house in Tisvilde, a peaceful coastal village where he often retreated for rest and quiet thinking. Frisch arrived and explained what he and his aunt had worked out, describing Hahn's experimental results and their theoretical interpretation. Bohr listened, and almost immediately grasped the full significance of what he was hearing. He reportedly struck his forehead and exclaimed that they had all been so foolish not to see this possibility before, that the liquid drop model made fission almost obvious once you thought about it properly. The division of a heavy nucleus into two lighter ones, with the accompanying release of energy, fit perfectly with the physical picture Bohr had been developing. But there was little time to linger over this realization, for Bohr had already made plans to travel to America for an extended visit, and his departure was imminent. In January of 1939, Bohr boarded the Swedish-American liner MS Drottningholm, bound for New York. Accompanying him was the Belgian physicist Leon Rosenfeld, a close collaborator who had worked with Bohr on questions of quantum mechanics and its interpretation. The crossing of the Atlantic took roughly a week, and during those days at sea, as the ship made its steady way westward through the winter ocean, Bohr worked intensively on the theoretical implications of nuclear fission. The Drottningholm was a comfortable passenger vessel, and Bohr and Rosenfeld had time for extended discussions in Bohr's cabin and in the ship's public rooms. Bohr's mind was racing ahead, considering what fission meant for the behavior of different uranium isotopes, for the possibility of chain reactions, for the future of nuclear physics itself. He paced and talked, sometimes lying on his cabin bunk staring at the ceiling while working through calculations in his head, and Rosenfeld served as a sounding board and assistant, helping to record and organize Bohr's rapid flow of ideas. By the time the ship approached the American coast, Bohr had developed a substantial theoretical framework for understanding the fission process. Upon arriving in New York, Bohr and Rosenfeld made their way to Princeton, where Bohr had arranged to spend several months at the Institute for Advanced Study. Here something of a small misunderstanding occurred. Bohr had intended to wait until Frisch and Meitner had published their theoretical interpretation before announcing the discovery of fission to the American physics community. But Rosenfeld, unaware of this intention, mentioned the news at a gathering of physicists shortly after their arrival. Word spread with remarkable speed through the close-knit community of nuclear physicists, and within days laboratories across America were rushing to confirm and extend the discovery. The Columbia University Laboratory, where Enrico Fermi was working, quickly verified that fission indeed occurred and detected the large energy release that Meitner and Frisch had predicted. At Princeton, Bohr began collaborating with John Archibald Wheeler, a young American physicist of considerable ability who would later make important contributions to general relativity and quantum mechanics. Together, Bohr and Wheeler worked to develop a comprehensive theoretical treatment of nuclear fission, building on the liquid drop model and incorporating the latest experimental data. Their central insight concerned the different behavior of the two main isotopes of uranium, uranium-235 and uranium-238. Natural uranium contains both isotopes, with uranium-238 being far more abundant, comprising more than 99% of the total, while uranium-235 makes up less than 1%. Bohr and Wheeler realized that these two isotopes would respond very differently to bombardment by neutrons. Uranium-235, they calculated, could be made to fission by neutrons of any energy, including the slow thermal neutrons that had been used in so many nuclear experiments. Uranium-238, on the other hand, would only undergo fission when struck by fast, high-energy neutrons, and even then less readily. This difference arose from the detailed quantum mechanical properties of the two nuclei, particularly the pairing of protons and neutrons and the resulting energy levels available to the compound nucleus. The implications of this finding were profound, for it suggested that a sustained chain reaction, in which the neutrons released by one fission event would trigger further fissions in a self-sustaining process, would be much easier to achieve with uranium-235 than with natural uranium. The Bohr-Wheeler paper setting out this theory was published in the Physical Review in September of 1939, by which time the world had changed dramatically. Germany had invaded Poland on the 1st of September, and Britain and France had declared war on Germany 2 days later. The Second Great War of the century had begun. Bohr, reading the news from Europe with growing concern, prepared to return to Denmark, uncertain of what he would find but determined to be with his institute and his colleagues during the crisis. The peaceful world of international scientific cooperation that he had worked so hard to build seemed to be crumbling around him. Bohr returned to Copenhagen in the autumn of 1939, sailing back across an Atlantic that was now a theater of naval warfare, with German submarines prowling the shipping lanes. Denmark itself remained neutral, hoping to avoid being drawn into the conflict, but this hope proved fragile. On the 9th of April, 1940, German forces invaded Denmark in a swift operation that met little resistance. By the end of that day, the country was under German occupation, its government forced to accept terms that preserved a degree of formal independence but left real power in German hands. For Bohr, the occupation presented an immediate and ongoing dilemma. He could have attempted to leave, to join the many European scientists who were finding refuge in America and Britain, but he chose instead to remain in Copenhagen. His reasons were several. He felt a responsibility to the institute that bore his name and to the many Danish and foreign scientists who worked there. He believed that by staying he might be able to protect them and to preserve something of the intellectual community he had spent decades building. There were also Jewish colleagues and staff members who might face persecution, and Bohr hoped that his international reputation and the Danish government's policy of protecting its Jewish citizens might provide some measure of safety. The years of occupation that followed would test these hopes severely, and Bohr would find himself navigating a treacherous path between collaboration and resistance, between protecting his institute and maintaining his integrity. But in those first months, as the spring of 1940 gave way to summer and the Germans consolidated their control, there was little to do but wait and watch and continue, as best one could, the quiet work of science in a world that had been overtaken by war. The institute remained open, seminars continued, and the rhythms of academic life persisted, even as the shadow of occupation fell across everything. When the German forces crossed the Danish border on the morning of the 9th of April, 1940, the occupation of Denmark began with a swiftness that left little time for resistance, and within a matter of hours the Danish government had chosen to accept the German presence rather than face the destruction that military opposition would surely bring, and so began a period of what historians would later call the policy of cooperation, in which Denmark maintained a degree of nominal independence while functioning under the watchful presence of German authority. And for Niels Bohr, working quietly at his institute in Copenhagen, this new reality required a careful recalibration of daily life, a navigation of constraints both spoken and unspoken, as he continued his scientific work within an atmosphere that had grown considerably more complicated than the peaceful years that came before. The Institute for Theoretical Physics on Blegdamsvej remained open during these early years of occupation, and Bohr continued to direct its activities with the same thoughtful attention he had always brought to his work, though the character of the Institute had necessarily changed, as many of the international visitors who had once filled its halls and contributed to its lively atmosphere of intellectual exchange were now scattered across the world or prevented from traveling by the circumstances of war, and Bohr found himself working within a smaller and more constrained community of physicists, yet still endeavoring to maintain some semblance of the collaborative spirit that had always defined his approach to scientific inquiry, even as the political situation outside the Institute's walls grew progressively more troubling with each passing month. During this period, Bohr devoted considerable energy to protecting colleagues of Jewish heritage who remained in Denmark or who had sought refuge there from persecution elsewhere in Europe, and he used what influence and connections he possessed to assist those who found themselves in danger, working through networks of trusted friends and allies to provide warnings, to arrange hiding places, and to facilitate escapes when circumstances demanded such measures. And though much of this work was necessarily conducted with discretion and has left only fragmentary traces in the historical record, it is clear that Bohr understood the moral obligations that accompanied his position of relative prominence, and that he acted upon those obligations with a quiet determination that would become more fully evident as the war progressed and the dangers facing Jewish Danes increased. It was during this unsettled time that one of the most discussed and debated episodes in the history of 20th-century physics occurred, an encounter that has generated more speculation and scholarly analysis than perhaps any other meeting between scientists. And this was the visit of Werner Heisenberg to Copenhagen in September of 1941, when the German physicist traveled to the occupied Danish capital ostensibly to deliver a lecture at the German Cultural Institute, though it was understood by all parties that the visit would provide an opportunity for Heisenberg to meet privately with his former mentor and longtime friend. And what transpired during their conversation has remained a subject of enduring mystery and considerable controversy in the decades since that autumn evening. Heisenberg arrived in Copenhagen as a representative, whether willingly or reluctantly, of a Germany that had conquered much of Europe and now occupied the country where Bohr lived and worked, and this fundamental asymmetry of circumstance inevitably colored their meeting, regardless of the personal affection and scientific respect that had once characterized their relationship. And when the two men walked together in the evening darkness, perhaps in the garden behind Bohr's residence at the Carlsberg mansion where he now lived, they entered into a conversation whose precise content would later be recalled quite differently by each of them, with the discrepancies between their accounts forming the basis of a historical puzzle that has never been definitively resolved. Heisenberg's version of events, as he recounted them in later years, suggested that he had sought to convey to Bohr certain intimations about the German nuclear research program, perhaps hoping to establish some form of understanding between physicists on both sides of the war regarding the development of atomic weapons. And according to this account, Heisenberg may have been seeking Bohr's counsel on questions of scientific ethics, or attempting to communicate that the German program was not progressing rapidly toward a bomb, or even exploring the possibility of some informal agreement among physicists to refrain from pursuing such weapons with full commitment, though the precise nature of his intentions has remained unclear even in Heisenberg's own various retellings of the episode. Bohr's recollection of the meeting differed markedly from Heisenberg's account, and in the years after the war, Bohr consistently maintained that he had come away from the conversation with the impression that Heisenberg was working actively toward the creation of atomic weapons for Germany, and that the younger physicist had spoken of this work with something approaching enthusiasm, or at least acceptance. And this understanding of the meeting left Bohr deeply troubled, and effectively ended the close friendship that had once existed between the two men. And though Bohr drafted several letters to Heisenberg in subsequent years attempting to address the matter and clarify his recollections, he never sent these letters during his lifetime, and they were discovered among his papers only after his death. The question of what Heisenberg truly intended during that September evening in Copenhagen, and what he actually said to Bohr as they walked together in the darkness of the occupied city, has been examined and debated by historians, physicists, biographers, and even playwrights in the years since, and various interpretations have been offered. some casting Heisenberg as a conflicted figure attempting to sabotage the German bomb effort from within, others portraying him as a physicist who had made his peace with serving the Nazi regime, and still others suggesting that the truth lies somewhere in the ambiguous territory between these positions. And what remains certain is only that the meeting occurred, that it was consequential for the relationship between these two remarkable scientists, and that its full meaning continues to elude definitive historical understanding, as if the uncertainty principle that Heisenberg himself had articulated years before in happier circumstances at this very institute had somehow extended itself into the realm of human memory and intention. As the years of occupation continued, the situation for Jewish Danes remained relatively stable compared to the persecution occurring elsewhere in German-controlled Europe, in part because the policy of cooperation allowed the Danish government to resist German demands for anti-Jewish measures. But this precarious protection could not last indefinitely, and by the autumn of 1943 the circumstances had begun to shift in ominous ways. With the Danish government's resignation in August following increased resistance activities and German imposition of martial law, and rumors began to circulate that the German authorities were preparing to act against the Jewish population of Denmark. It was in late September of 1943 that these rumors crystallized into specific warning, when Georg Ferdinand Duckwitz, a German diplomat attached to the German legation in Copenhagen, took the extraordinary step of informing Danish political contacts that a raid to arrest and deport Danish Jews was planned for the night of the 1st of October. And this information spread rapidly through networks of resistance and community organizations, reaching Bohr and his family along with thousands of other Danish Jews in the days before the planned roundup. And suddenly the Bohr family found themselves facing immediate personal danger. For Niels Bohr's mother, Ellen Adler Bohr, had been Jewish, which meant that under the racial classifications imposed by the German authorities, Bohr and his brother Harold and their families were subject to deportation to the concentration camps from which so few returned. The warning that reached the Bohr family left no time for hesitation or elaborate planning, and preparations for escape began immediately, with the understanding that remaining in Copenhagen would mean almost certain arrest when the German action commenced. And across Denmark in those final days of September, a remarkable and largely spontaneous rescue effort was taking shape, as ordinary Danes organized to help their Jewish neighbors and countrymen reach the coast and cross the narrow waters of the Øresund Strait to neutral Sweden, where safety awaited those who could complete the dangerous journey. On the evening of the 29th of September, 1943, Niels Bohr and his wife Margrethe, along with his brother Harold, made their way to the Danish coast where a fishing boat was waiting to carry them across the strait to Sweden, and the crossing was accomplished in darkness to avoid German patrol boats, the small vessel moving quietly through waters that had become a passage to survival for thousands of fleeing refugees during those extraordinary October days. And when the boat reached Swedish shores, the Boers found themselves safe but separated from their homeland by circumstances of war and persecution. Upon reaching Sweden, Bohr did not allow himself to rest in the relative comfort of his own safety while his countrymen remained in danger, and he immediately sought an audience with King Gustav V of Sweden to advocate for the protection of Danish Jews still attempting to escape. And during this meeting, Bohr urged the Swedish king to make a public declaration offering asylum to all Danish refugees, an appeal that contributed to the Swedish government's decision to formally announce that all Danish Jews would be welcome in Sweden. And this public commitment helped encourage the continuation of the rescue effort and provided reassurance to those still attempting the dangerous crossing. The rescue of Danish Jews during October of 1943 stands as one of the most remarkable episodes of civilian resistance during the Second World War. With approximately 7,700 of the 8,000 Jews living in Denmark successfully reaching Sweden through the efforts of fishermen, resistance members, and ordinary citizens who risked their own safety to help their neighbors escape, and Bohr's advocacy with the Swedish king, though representing only one element of this larger collective effort, demonstrated his continued commitment to using whatever influence he possessed in service of those facing persecution. While Bohr was in Sweden, word reached him through British channels that his expertise was urgently needed for war work of the highest importance, and an invitation was extended for him to travel to Britain to contribute to a project whose nature was not fully specified, but which clearly related to the applications of nuclear physics that Bohr understood all too well. And after careful consideration, Bohr agreed to make the journey, though the means of transportation that could be arranged presented considerable difficulties and no small degree of physical danger. On the 6th of October, 1943, Bohr boarded a British de Havilland Mosquito aircraft for the flight from Sweden to Britain, and this aircraft, designed primarily as a fast bomber, was not configured to carry passengers in any conventional sense, and Bohr was placed in the bomb bay of the aircraft, lying in a space that had been only minimally adapted for human occupancy, wearing a flight suit and helmet with oxygen equipment and intercom connections that would allow communication with the pilot during the high-altitude journey over German-occupied Norway and the North Sea. The flight proceeded at high altitude to avoid German interceptors, which necessitated the use of supplemental oxygen, and at some point during the journey Bohr was meant to receive instructions through the intercom to activate his oxygen supply, but the helmet he had been given did not fit properly over his rather large head, and the earphones were not positioned correctly against his ears, and consequently Bohr did not hear the pilot's instructions and did not switch on his oxygen supply as the aircraft climbed to altitude. And as the minutes passed, Bohr lost consciousness from hypoxia, slipping into an oxygen-deprived state that could have proved fatal if it had continued much longer. It was only when the aircraft descended to lower altitude as it approached Britain that sufficient oxygen became available for Bohr to regain consciousness, and the pilot, unaware of the crisis that had been unfolding in the bomb bay behind him, landed the aircraft safely, and Bohr emerged from this harrowing journey alive but quite shaken by the experience, having come closer to death during those oxygen-deprived minutes than perhaps at any other time in his life. And yet he had completed the journey from occupied Europe to Britain, where his contributions to the Allied war effort would soon begin in earnest, and where the next chapter of his remarkable life would unfold amid the unprecedented scientific undertaking that was already well underway in laboratories on both sides of the Atlantic. In the autumn of 1943, a fishing boat slipped away from the Danish coast under cover of darkness, carrying among its passengers a man whose name was known to physicists around the world, though for the purposes of this journey he would answer to a different name entirely. Niels Bohr had escaped occupied Denmark just weeks earlier, spirited away to Sweden when word reached him that the German authorities intended to arrest him along with other Danish citizens of Jewish heritage, and now he was being brought to England at the urgent request of the British government, who had matters of considerable scientific importance to discuss with him. He travelled under the code name Nicholas Baker, a pleasantly ordinary English name chosen precisely because it bore no resemblance to his own, and accompanying him was his son Arj, a young physicist in his own right, who had been assigned the complimentary alias of James Baker, so that father and son might pose as unrelated colleagues should anyone inquire too closely into their business. The journey from Sweden to Scotland was made by aircraft, a Mosquito bomber modified to carry passengers in its empty bomb bay, and the flight proved rather more eventful than anyone had hoped, for when the aircraft climbed to high altitude to avoid German fighters, the oxygen mask provided to Bohr failed to function properly, and he lost consciousness for a portion of the flight, though he recovered well enough once the plane descended and landed safely on British soil. This brush with danger seemed not to have diminished his spirits particularly, and within days he was being briefed by British officials on a project of such secrecy that even its name was spoken carefully and only among those who had been properly cleared to hear it. The British called their atomic research effort tuberlois, a deliberately bland designation chosen to obscure the true nature of the work, and Bohr learned for the first time the full scope of what Allied scientists had accomplished in the years since war had closed the borders between nations. In December of 1943, Nicholas Baker and James Baker crossed the Atlantic Ocean and arrived in the United States of America, where the scale of the atomic enterprise exceeded anything Bohr had imagined during his years of isolation in Copenhagen. The Americans had gathered an extraordinary collection of scientific talent at various sites across the country, channeling vast industrial resources toward the construction of facilities that could produce fissionable material in quantities sufficient for a weapon of unprecedented destructive power. Bohr was taken to meet with General Leslie Groves, the military officer who oversaw the entire Manhattan Project, and with J. Robert Oppenheimer, the theoretical physicist who directed the secret laboratory that had been established in the high desert of New Mexico at a place called Los Alamos. The security apparatus surrounding the project was elaborate and sometimes bewildering, with compartmentalized information and false names and careful protocols governing who might speak to whom about which particular aspects of the work. And Bohr dutifully signed himself into the Los Alamos facility as Nicholas Baker, mathematician, maintaining the fiction even in official records that only a handful of people would ever see. His role at Los Alamos was somewhat unusual, for at 58 years of age he was considerably older than most of the physicists working feverishly on the theoretical and practical problems of bomb design, and the specific technical challenges being addressed had moved beyond the areas where his own expertise was most directly applicable. Yet his presence proved valuable in ways that transcended any particular calculation or experimental result. The younger scientists at Los Alamos had grown up reading his papers and learning quantum mechanics through the framework he had helped to create, and to have Bohr walking among them, sitting in on seminars, asking his characteristically probing questions, and offering his gentle encouragement, provided a kind of reassurance that what they were doing was being witnessed and understood by one of the great minds of their discipline. He served as what one might call a senior consultant and morale booster, a figure whose very presence lent gravity and continuity to an endeavor that often felt frantic and improvisational despite its enormous consequences. Oppenheimer later recalled that Bohr seemed to function as a kind of scientific father-confessor at Los Alamos, someone to whom the younger physicists could bring not only their technical puzzles but also their deeper uncertainties about the moral dimensions of their work. The bomb they were building would kill many thousands of people if it succeeded, and the scientists working on it lived with this knowledge even as they bent their efforts toward making the weapon as effective as possible. Bohr listened to their concerns with his characteristic attentiveness, neither dismissing their qualms nor offering false comfort, and his presence seemed to help many of them find their way through the ethical complexities of their situation. His son Arj worked alongside him during these months, assisting with calculations and serving as a sounding board for his father's thoughts, the two of them maintaining their Baker aliases throughout their time at the laboratory in the mountains. But as the work progressed and the likelihood of a successful weapon grew more certain, Bohr found his own thoughts turning increasingly toward what would happen after the war ended and the atomic secret became known to the wider world. He understood perhaps better than most that the physics underlying the bomb was not itself secret, that scientists in other countries would eventually work out the same principles and develop their own weapons, and that the result would be an arms race of terrifying proportions unless something were done to prevent it. The temporary monopoly that the Americans and British would enjoy after deploying the weapon could not last, and Bohr believed that the interval before other nations acquired their own bombs represented a precious window of opportunity during which the foundations of international cooperation might be established. He began advocating, in conversations with anyone who might listen, for what he called an open-world approach to atomic energy, in which the great powers would share information and submit to mutual inspection rather than retreating into secrecy and suspicion. In August of 1944, Bohr secured a meeting with President Franklin Roosevelt to discuss these ideas, presenting his arguments for international control of atomic energy and warning that failure to reach accommodation with the Soviet Union would lead inevitably to a dangerous post-war competition. Roosevelt listened courteously and seemed receptive to at least some of what Bohr had to say, though he made no commitments and offered no clear indication of how American policy might develop after the war. Encouraged by this meeting, Bohr sought also to persuade the British, and in September of the same year he met with Prime Minister Winston Churchill at Downing Street, hoping to find similar openness to his proposals. The meeting did not go well at all. Churchill was impatient and dismissive, barely allowing Bohr to complete his sentences before interrupting, and he seemed to regard the physicist's proposals as dangerously naive at best and potentially treasonous at worst. The Prime Minister appeared to believe that Bohr might be advocating the sharing of atomic secrets with the Soviet Union, and he suggested afterward that perhaps the Danish scientist ought to be confined or imprisoned to prevent him from doing mischief. Nothing came of Churchill's dark suspicions, but the experience left Bohr shaken and concerned about the direction that post-war atomic policy might take. He continued to refine his arguments, working with his son Arj on drafts of memoranda that articulated his vision of international cooperation and the open exchange of information as the only alternative to a catastrophic arms race. These memoranda, sometimes called the Arj-Nielsen drafts after one of the aliases used in their preparation, laid out in careful detail the case for abandoning secrecy in favor of transparency, arguing that the temporary advantages of monopoly were far outweighed by the long-term dangers of a world divided into hostile camps, each possessing weapons capable of destroying civilization. The memoranda circulated among a small number of officials and scientists, but they failed to alter the fundamental trajectory of Allied policy, which continued to prioritize secrecy and the preservation of the Anglo-American atomic advantage for as long as possible. The war in Europe ended in May of 1945, and Denmark was liberated from German occupation, allowing Bohr at last to return to the city and the institute he had been forced to abandon nearly 2 years earlier. He arrived in Copenhagen in August of that same year, just days after the atomic bombs had been dropped on Hiroshima and Nagasaki, bringing the Pacific War to its abrupt and terrible conclusion and demonstrating to the entire world the reality of the weapon that had been developed in such secrecy. The mushroom clouds that rose over those Japanese cities seemed to vindicate everything Bohr had warned about, making viscerally clear the stakes of the atomic age that humanity had now entered. And he threw himself into the work of post-war advocacy with renewed urgency, believing that the window for establishing international control was closing rapidly. The institute in Copenhagen required considerable effort to rebuild and restore to its former vitality, for the years of occupation had disrupted its work and scattered many of its researchers to other countries. Bohr devoted himself to this task with characteristic energy, reconnecting with physicists around the world and resuming the international conferences that had made Copenhagen such an important center of scientific exchange before the war. Young physicists began once again to make the pilgrimage to Denmark, seeking out the conversations and the intellectual atmosphere that Bohr's institute had always provided, and slowly the threads of international collaboration were rewoven across the boundaries that the war had established. The work of physics continued, as it always does, with new questions emerging from the answers that had been found and new generations of researchers taking up the investigations that their predecessors had begun. In June of 1950, Bohr published an open letter addressed to the United Nations, setting forth in public the arguments for international atomic cooperation that he had been making in private for the past 6 years. The letter called upon the nations of the world to recognize that the atomic age demanded new forms of organization and new commitments to transparency, warning that the alternative was an arms race that would consume vast resources and place all of humanity under the shadow of annihilation. He advocated for the open exchange of scientific information, for international inspection regimes that would build confidence and prevent secret weapons programs, and for the eventual elimination of atomic weapons entirely once trust had been established between the major powers. The letter received considerable attention and helped to shape the emerging discourse around nuclear arms control, though the Cold War was already well underway and the hopes for immediate international cooperation were fading in the face of deepening suspicion between East and West. Bohr also played a founding role in the establishment of CERN, the European Organization for Nuclear Research, which was created in the early 1950s to provide European physicists with access to particle accelerators and other expensive experimental facilities that no single nation could afford to build and operate alone. The organization represented precisely the kind of international scientific cooperation that Bohr had long advocated, bringing together researchers from countries that had so recently been at war with one another and demonstrating that science could serve as a bridge between nations rather than a source of division. He participated in the planning discussions and lent his prestige to the effort, helping to secure the political and financial support necessary to bring the laboratory into existence, and he lived to see the first experiments conducted at the facility in Geneva. The Atoms for Peace program, launched by the American government in the 1950s as an effort to promote the peaceful uses of atomic energy, also engaged Bohr's attention and involvement, for it aligned in some respects with his vision of an open world in which nuclear knowledge would be shared for the benefit of all humanity rather than hoarded for military advantage. He participated in conferences and contributed to discussions about how atomic energy might be harnessed for power generation and medical applications and other constructive purposes, lending his voice to the effort to demonstrate that the atom held promise as well as peril. The program had its limitations and its critics, and the arms race that Bohr had warned about continued unabated despite the rhetoric of peaceful cooperation. But he persisted in his advocacy nonetheless, believing that every step toward openness and collaboration was valuable even if the ultimate goal remained distant. Throughout these post-war years, the Institute in Copenhagen continued to flourish under Bohr's direction, attracting talented physicists from around the world and hosting the conferences and discussions that had always been central to its mission. The conversations that had begun in the 1920s, when the foundations of quantum mechanics were being laid, continued now in a world transformed by the practical applications of atomic physics, and Bohr remained at the center of these conversations, listening more than speaking, asking his careful questions, and guiding younger researchers toward clarity in their thinking. The institute that bore his name had become an institution, a place where the traditions of scientific inquiry that he embodied were passed down from generation to generation, and he watched with quiet satisfaction as the work continued and the understanding deepened. As the 1950s began, Niels Bohr had reached his 65th year, and though he had long since established himself as one of the most consequential figures in the history of physics, he showed no inclination whatsoever to step back from active engagement with the scientific community he had done so much to shape. The Institute on Blegdamsvej continued to hum with activity, younger researchers arriving from across the world to work within its modest walls, and Bohr remained at the center of this intellectual enterprise, welcoming visitors, attending seminars, and offering his characteristic combination of probing questions and gentle encouragement to all who sought his counsel. The building itself had grown somewhat since its founding 3 decades earlier, with additional wings and facilities added to accommodate the expanding scope of modern physics research. Yet it retained that essential quality of informality and openness that Bohr had cultivated from the very beginning, a place where hierarchy mattered less than ideas, and where even the most junior student might find themselves in conversation with distinguished professors over coffee in the common room. During this period, Bohr devoted considerable energy to questions of nuclear structure, returning to a domain he had first explored in the 1930s with his compound nucleus model. Working in close collaboration with his son Arj, who had become a physicist of considerable distinction in his own right, and with the American-born theorist Ben Modelsorn, who had settled in Copenhagen after completing his doctoral studies, Bohr helped develop what became known as the collective model of the atomic nucleus. This theoretical framework sought to reconcile 2 apparently contradictory pictures of nuclear behavior, one in which individual nucleons moved independently within the nucleus much as electrons orbit in an atom, and another in which the nucleus behaved as a collective whole, somewhat like a droplet of liquid capable of vibration and deformation. The work of Bohr, Modelsorn, and Arj Bohr demonstrated that both pictures contained essential truths, that the nucleus exhibited properties characteristic of independent particle motion, while simultaneously displaying collective behaviors that emerged from the coordinated movement of many nucleons together. This synthesis proved remarkably fruitful for understanding nuclear phenomena, explaining patterns in nuclear energy levels and transitions that had previously seemed puzzling, and the approach would eventually be recognized as a major contribution to nuclear physics. In 1955, the world witnessed an event that would have seemed quite impossible just a decade earlier, when representatives from nations across the globe gathered in Geneva for the first international conference on the peaceful uses of atomic energy, an assembly that became known informally as the Atoms for Peace Conference. This remarkable meeting brought together scientists and officials from both sides of the increasingly rigid Cold War divide, creating for a brief moment a space where the international character of science could reassert itself against the pressures of political antagonism. Bohr, then approaching 70 years of age, attended the conference and addressed the assembled delegates, speaking on matters related to atomic energy and its potential applications for human welfare. His presence carried particular significance given his long advocacy for international cooperation and open exchange of scientific information, themes he had pursued so earnestly in his wartime memoranda and post-war public statements. The Geneva Conference represented, if not the full realization of Bohr's vision for an open world transformed by atomic knowledge, at least a meaningful step toward the kind of international scientific dialogue he had championed, and he participated with evident satisfaction in what felt like a vindication, however partial, of his persistent optimism about human capacity for reasonable cooperation. 2 years later, in 1957, Bohr played a central role in establishing the Nordic Institute for Theoretical Physics, known by its acronym NORDITA, which was founded in Copenhagen as a collaborative venture among the Scandinavian nations to promote advanced research and training in theoretical physics. The institute represented an extension of the cooperative spirit that had always characterized Bohr's approach to science, creating a framework through which Denmark, Norway, Sweden, Finland, and eventually other Nordic countries could pool their resources and expertise in support of fundamental research. NORDITA was established in close proximity to Bohr's own institute, allowing for natural interaction between the two institutions and ensuring that the new venture would benefit from the intellectual atmosphere that had made Copenhagen such a vital center for physics. Bohr served as the first chairman of the Nordea board, lending his prestige and experience to the fledgling organization as it found its footing, and the institute would go on to become an important fixture in the European physics landscape, training generations of theorists and hosting countless visitors from around the world. That same year, 1957, brought another honor to Bohr when he received the first Atoms for Peace Award, established by the Ford Foundation to recognize outstanding contributions to the peaceful applications of atomic energy. The award carried a substantial monetary prize and considerable prestige, and Bohr accepted it as recognition not merely of his own scientific achievements but of the broader vision for atomic energy that he had articulated so persistently over the preceding years. The ceremony provided an occasion for reflecting on how far the world had come since those desperate wartime years when the destructive potential of nuclear fission had first been realized, and yet also for acknowledging how much remained to be done before the peaceful promise of atomic energy could be fully realized for the benefit of humanity. Throughout these later years, Bohr continued to live at the Carlsberg honorary residence, that magnificent mansion in Copenhagen which had been provided to him and his family since 1932 by the Carlsberg Foundation. The residence, known as the House of Honor, was traditionally offered to whichever Danish citizen was deemed to have brought the greatest distinction to the nation, and Bohr had occupied it for 3 decades, raising his children within its gracious rooms and receiving countless visitors in its elegant parlors. The house contained a remarkable collection of art assembled by the brewing magnate Carl Jacobsen, paintings and sculptures of considerable distinction that surrounded the Bohr family with beauty as they went about their daily lives. Margrethe presided over this household with quiet competence, ensuring that the endless stream of visitors found welcome and refreshment, managing the practical details that allowed Bohr to focus his energies on scientific and philosophical matters. The residence also featured extensive gardens where Bohr liked to walk with guests. Continuing conversations began indoors as they strolled among the carefully tended plantings, and it was in these surroundings that much of the informal scientific exchange that characterized the Copenhagen spirit took place. Bohr's philosophical writings continued through the 1950s, as he sought to extend and refine the concept of complementarity that had been his central contribution to the interpretation of quantum mechanics. He explored applications of complementary thinking to questions in biology, considering how the peculiar relationship between living organisms and the physical processes that sustain them might require similar tolerance for apparently contradictory descriptions. He wrote on epistemological questions more broadly, examining the relationship between observer and observed, between the instruments of measurement and the phenomena being measured, always returning to that fundamental insight that the conditions of knowledge themselves shape what can be known. These philosophical essays were characteristically dense and carefully qualified, each sentence laden with subordinate clauses and careful distinctions, and they demanded close attention from readers accustomed to more straightforward exposition. Yet for those willing to engage with Bohr's demanding prose, the rewards were substantial, offering a perspective on the nature of physical reality and human understanding that remained provocative and influential long after his death. In 1961, Bohr made a final visit to the Soviet Union, traveling to meet with Soviet physicists who had been his colleagues in the international community of science before political barriers had made such exchanges so difficult. The visit represented a kind of return to an earlier era, when scientists moved freely across national boundaries in pursuit of shared understanding, and Bohr's presence served as a reminder of the human connections that persisted beneath the surface of Cold War tensions. He met with old friends and former students, discussed recent developments in physics, and embodied through his very presence that internationalist vision of science that had always been central to his conception of the scientific enterprise. The following year, on November 18, 1962, Niels Bohr passed away at his home in the Carlsberg residence, succumbing to heart failure at the age of 77. The end came peacefully, in familiar surroundings, with his beloved Margrethe nearby after more than 50 years of partnership. In the days leading up to his death, Bohr had been engaged as always with scientific questions, continuing to think about problems that had occupied him for decades, and on the blackboard in his study there remained an unfinished drawing when the end came. This final sketch depicted the photon box thought experiment that Einstein had proposed more than 30 years earlier at the 1930 Solvay conference, that ingenious contraption with its clock and weighing scale by which Einstein had hoped to circumvent the uncertainty principle. Bohr had responded to that challenge brilliantly at the time, showing how general relativity itself rescued quantum mechanics from Einstein's attack, and the image had evidently remained with him across all the intervening years, a symbol perhaps of that profound intellectual friendship and rivalry that had shaped so much of his thinking about the foundations of physics. The unfinished drawing on the blackboard seemed to suggest that Bohr's engagement with these deep questions continued literally until his final hours, that the conversation with Einstein, though Einstein himself had died 7 years earlier, somehow persisted in Bohr's mind as an ongoing dialogue about the nature of reality and the limits of human understanding. The funeral service was held at the Copenhagen Cathedral, that ancient church in the heart of the Danish capital where generations of the nation's most distinguished citizens had been commemorated. Colleagues and former students gathered alongside family members and representatives of the Danish government to pay their respects to a man who had done so much to advance human knowledge and to elevate Denmark's standing in the world of science. Following the service, Bohr's remains were interred at a cistern cemetery in the Nørrebro district of Copenhagen, a burial ground that also holds the remains of Hans Christian Andersen and Søren Kierkegaard, placing Bohr in the company of Denmark's greatest cultural figures. He was laid to rest near other members of his family, including his father Christian Bohr, in a plot that would later receive Margrethe as well when she died several years later. The partners of half a century reunited in that quiet corner of the cemetery. The legacy that Bohr left behind extended far beyond his own scientific contributions, substantial as those were. The institute that bore his name, renamed the Niels Bohr Institute in 1965 in tribute to its founder, continued as a major center for physics research, training new generations of scientists and maintaining the collaborative spirit that had always characterized its operations. The many students who had passed through Copenhagen over the decades carried Bohr's approach to physics into their own careers, establishing research programs and teaching methods that reflected the lessons they had learned in that informal, question-driven atmosphere. The Copenhagen interpretation of quantum mechanics, though it would face challenges from alternative formulations in subsequent decades, remained the dominant framework within which most physicists understood the quantum world, shaping textbooks and classroom instruction and the everyday practice of physical science. Bohr's philosophical contributions, particularly the concept of complementarity, continued to provoke discussion and debate among those interested in the foundations of physics and the nature of scientific knowledge more broadly. Perhaps the most touching testament to Bohr's enduring influence came in 1975, when his son Arj Bohr, together with Ben Modelsorn and the American physicist James Rainwater, received the Nobel Prize in Physics for their work on the collective model of nuclear structure. This recognition of the younger Bohr's achievements represented a remarkable continuation of a scientific tradition, father and son both honored with the highest distinction in physics, and it reflected the lasting importance of the work on nuclear structure that the three collaborators had pursued in Copenhagen during the 1950s. Bohr, like his father before him, had dedicated his career to understanding the fundamental workings of matter, and the prize he received validated both his own contributions and the broader Copenhagen tradition of which he was a part. And so, as you settle deeper into rest this evening, perhaps you might carry with you the image of that unfinished blackboard drawing, the photon box that Einstein had imagined and Bohr had pondered for more than 3 decades, a testament to a lifetime of questioning and a friendship of minds that transcended even death. The mansion at Carlsberg stands quiet now, the art collection still gracing its walls, and the Institute on Blegdamsvej continues its work, welcoming visitors from around the world just as it did when Bohr walked its corridors. There is something deeply restful in the thought of such continuity, the way that scientific understanding passes from teacher to student across generations, the way that questions raised in one decade find answers in the next and raise new questions in their turn. The gentle accumulation of knowledge proceeds in its unhurried fashion, much as it did in Bohr's day and will continue to do long after our own time has passed, a patient enterprise requiring many hands and many minds, each contributing what they can to the common endeavor of understanding this strange and beautiful universe we find ourselves inhabiting.